Welcome, dear listener, to The Sleepy Scientist. This is a place where curiosity and calm walk hand in hand, designed to help you drift toward rest while exploring the quiet wonders of the universe. Tonight, we'll be turning our attention to a fiery spectacle far above our heads, the restless bursts of light and energy we call solar flares. They are the sun's own fireworks, dazzling displays that ripple through space and sometimes even reach down to touch our world in subtle and surprising ways. Before we begin our journey, I would love to know where you're listening from. Are you curled up beneath warm blankets, perhaps with the night sky outside your window? Or are you in another corner of the world where the sun itself is still shining? Share your place in the world below. It is always fascinating to see the tapestry of listeners spread across Earth. If you find these quiet explorations soothing, please do consider leaving a like and subscribing. It helps this channel grow, and it means you'll have more gentle science stories waiting whenever you need them. To those of you already subscribed, thank you. Your presence here keeps these journeys alive, and while I do hope this helps you fall asleep, there is always the small risk that the story may become so interesting that you stay awake. If that happens, at least the night will gift you knowledge as well as rest. And one more thing, if you haven't already, please consider checking out my new YouTube channel, The Sleepy Geographer. The link will be in the description for the video. So let us begin with a question to guide us. What secret storms brew on the surface of our sun, hidden beneath its calm glow, waiting to erupt into cosmic fireworks? The sun is often thought of as a steady companion, rising and setting with reassuring rhythm, but this familiar star is anything but quiet. Beneath its golden light, immense forces twist and build, storing energy in ways that can only remain hidden for so long. When that energy is suddenly released, we see what we call a solar flare, a dazzling outburst that pours radiation into space in a flash, brighter than billions of nuclear bombs. These flares are not rare. In fact, they are part of the sun's restless nature, tied to cycles of magnetism and the dance of plasma across its surface. Yet while they may sound frightening, they are also strangely beautiful, a reminder that even the most constant presence in our lives carries a secret life of turbulence. Scientists watch them closely, not only to understand our own star, but to better predict the ways it might touch our planet, sometimes with nothing more than a gentle ripple of radio static, and sometimes with the power to disrupt satellites, power lines, and the glowing curtains of auroras across the poles. As we move through this exploration, we'll look at solar flares from every angle. Their birth, their dazzling light, the history of storms that once shook Earth, and the ways modern science works to keep a watchful eye on our star. Along the way, we'll find not just facts, but also wonder, because in many ways, solar flares are not merely threats or curiosities, but living reminders of how alive the universe really is. And so, as you settle into the comfort of your evening, let your thoughts drift outward to that great golden star above. For though it may feel calm from our quiet vantage point, the sun is a place of constant drama, and its fireworks are worth understanding. From the moment you first open your eyes in the morning, the sun feels like a constant. It rises without fail, bathes the world in light, and sets in a predictable arc that has comforted humanity for countless generations. To the casual observer, it's a perfect circle in the sky, unchanging and serene. Yet behind this calm exterior, the sun is anything but still. It is a restless star, an immense sphere of hot plasma, endlessly shifting and roiling in ways that are both violent and beautiful. The sun is a vast nuclear engine, a fusion reactor sustained by unimaginable pressure at its core. Deep within, hydrogen atoms are pressed together until they merge to form helium, releasing energy that slowly migrates outward over thousands of years before it finally escapes into space as light and heat. This energy fuels life on Earth, but it also stirs the outer layers of the sun into a perpetual state of motion. The surface you see shining in the sky is not a solid shell but a seething ocean of plasma. a soup of charged particles, constantly churned by convection and wrapped in magnetic fields. It is these magnetic fields that give the Sun its restless character. Unlike Earth, whose magnetic field is generated deep in its core and remains relatively stable, the Sun's magnetic field is tangled, twisted, and always changing. The plasma that makes up the Sun's body is electrically conductive, and as it moves, it drags magnetic fields with it, stretching and distorting them into elaborate knots. At times, these fields break through the surface, forming dark blemishes known as sunspots. To the naked eye, sunspots may look small, but many of them are vast enough to swallow Earth several times over. They are darker than the surrounding surface because they are cooler, though still blisteringly hot by human standards. Sunspots are not merely cosmetic marks on the Sun. They are signals of intense magnetic activity brewing beneath the surface, harbingers of the flares and storms that will later erupt. When clusters of sunspots appear, it is a sign that the Sun is in a more active phase of its natural rhythm, a cycle that has fascinated astronomers for centuries. This rhythm, known as the solar cycle, lasts about 11 years. During the peak of this cycle, called solar maximum, sunspots multiply, flares become frequent, and the Sun reveals its volatile temperament. At solar minimum, in contrast, sunspots fade away, and the Sun appears relatively calm. This cycle was first recognized in the mid-19th century, when careful observers noticed that sunspot activity waxed and waned with regularity. Since then, scientists have connected the cycle to the underlying machinery of the Sun's magnetic field. Roughly every 11 years, the Sun's magnetic poles flip, north becoming south and south becoming north, like a cosmic pendulum. This reversal drives the rise and fall of sunspots and flare activity, making the solar cycle a heartbeat of sorts. Not perfectly regular, but a rhythm that guides the star's restless energy. To imagine the Sun's surface is to picture an environment in constant motion. Granules of plasma rise and fall in convection, like boiling water in a pot, each one larger than a continent. Above these granules, bright arcs of plasma loop into space, tracing the shape of magnetic fields that stretch out like invisible scaffolding. From time to time, these magnetic fields snap and reconnect, releasing energy in explosive flashes. Even when no such drama is visible, the surface itself is alive, textured and shifting, never quite the same from one moment to the next. For centuries, humanity could only guess at this hidden turbulence. To the ancients, the Sun's face was flawless, a perfect divine disk in the heavens. The invention of the telescope in the early 17th century revealed a different truth. Astronomers like Galileo Galilei sketched sunspots drifting across the Sun's face, proving that our star rotated and that its light was not as pure as once believed. These observations challenge both science and philosophy, suggesting that even the most constant celestial body was flawed, dynamic, and alive. What was once a symbol of perfection became a source of endless questions. Today, with modern instruments, we can watch the Sun in incredible detail, peering at it across every wavelength of light. Specialized spacecraft capture images of its surface in extreme ultraviolet and X-rays, showing a world that looks nothing like the golden orb we see from Earth. In these wavelengths, the Sun blazes with loops of plasma and storms of energy, like a restless furnace wrapped in glowing tendrils. The calm circle of daylight is revealed to be a canvas of turbulence. The Sun's restlessness is not confined to its surface. Above it lies the corona, an atmosphere of plasma that extends millions of kilometers into space. Strangely, this corona is hotter than the surface itself, a mystery that has puzzled scientists for decades. Some of the energy released in the tangled magnetic field seems to funnel upward, heating the corona to millions of degrees. It is in this domain that the Sun's storms grow and evolve, the birthplace of the flares and eruptions that ripple through the solar system. This ceaseless activity is both a gift and a threat. Without the sun's energy, life on Earth would not exist. Yet the very dynamism that sustains us also holds the potential to disrupt our technology and remind us of our vulnerability beneath its gaze. It is a paradox. The same restlessness that fuels life can also, in sudden bursts, reach out across the void with disruptive force. Yet there is something comforting in knowing that our star is alive in this way. The sun is not a static lamp, but a dynamic being. Its cycles and storms are kind of breathing. Just as Earth has its seasons, its weather, and its rhythms, the sun too has its own patterns, larger and slower, but no less real. Its surface may look calm from our vantage point, but beneath that calm lies a symphony of motion, a reminder that even constancy is built on change. When you look up at the sun, carefully and always with protection, you're not seeing a frozen image in the sky. You're looking at a star in motion, a restless neighbour whose heartbeat shapes the environment of the solar system. It is an ever-turning engine of light, carrying within it the balance of creation and disruption, of beauty and danger. To understand it is to recognise that even the most familiar part of our world is still full of mystery, still teaching us that stability is an illusion, and that even the brightest constants in our lives are, at their core, endlessly restless. Imagine for a moment the sun's surface as a restless ocean of fire. Waves of plasma rise and fall, immense streams of charged particles churn and twist, and invisible magnetic fields tangle together like an endless knot. From our safe distance, it looks like a calm golden disk, but up close it is more like a turbulent sea with storms brewing at every moment. Within this roiling chaos lies the birthplace of one of the most dramatic events in the solar system, the solar flare. To understand how a flare is born, it helps to first grasp what the sun is made of. Unlike Earth, which is solid and rocky on the outside, the sun is composed almost entirely of plasma. Plasma is often called the fourth state of matter, alongside solid, liquid, and gas. It is what happens when gas becomes so hot that its atoms break apart, leaving behind a soup of freely moving ions and electrons. Because these charged particles respond strongly to magnetic fields, plasma is not just a chaotic fluid. It is a conductor, and in the sun it conducts electricity and magnetism on a truly colossal scale. Now, here is where things get interesting. As hot plasma flows around the sun, dragged by convection currents rising and falling beneath the surface, it pulls magnetic field lines along with it. Imagine invisible strings threaded through a boiling cauldron, constantly being stretched, knotted, and tangled. Over time, these magnetic field lines twist and warp until the stress becomes unbearable. At a certain point, the lines snap and rearrange themselves into a more stable pattern. This sudden rearrangement is known as magnetic reconnection, and it is the central engine behind every solar flare. Magnetic reconnection is one of those beautiful quirks of physics that sounds almost simple in words, but unfolds with stunning power in reality. Picture two magnetic fields pointing in opposite directions, pressed up against each other like two stubborn dancers refusing to move in sync. The energy trapped between them builds and builds until finally the tension releases. In an instant, the magnetic field lines break and reconnect in a new formation, releasing enormous amounts of energy. On the sun, this process unleashes radiation across the electromagnetic spectrum, accelerates particles to near the speed of light, and hurls plasma arcs high into the corona. The scale of this release is staggering. A single strong solar flare can release energy equivalent to billions of nuclear bombs exploding at once. Yet it all begins with invisible lines of force rearranging themselves in a way that physics demands. It is like a cosmic rubber band that has been twisted beyond its limit and finally snaps back. Except this rubber band lights up half a star and rattles planets millions of kilometers away. For astronomers, watching this process unfold is both mesmerizing and crucial. Instruments that peer at the sun in X-rays and extreme ultraviolet reveal loops of plasma tracing out the magnetic fields. Before a flare, these loops twist together like braids pulled too tightly. Then, as reconnection occurs, bright flashes spread along the loops, and plasma erupts outward in great arcs. It happens on timescales of minutes, sometimes even seconds, transforming magnetic stress into dazzling energy. What makes magnetic reconnection particularly fascinating is that it is not confined to the Sun. The same process happens in Earth's own magnetosphere, where it fuels auroras by funneling solar wind particles down into our atmosphere. It happens in laboratory plasmas, where scientists try to recreate and understand it. It even plays a role in the design of fusion reactors, where controlling plasma means learning how to live with the same physics that drives solar flares. The Sun simply performs it on a much grander, more explosive stage. The birthplace of a solar flare is often a region marked by sunspots. These dark patches are where magnetic fields have bundled tightly together, pushing through the surface and forming a tangled mess of loops and arcs. Astronomers sometimes call them active regions, and the name fits. Within these regions, the magnetic field is twisted like an overwound spring, and eventually something has to give. When it does, the flare bursts forth, sending energy racing outward across space. What we see from Earth depends on the wavelength of light we look at. To the human eye, a solar flare might only appear as a subtle brightening on the Sun's surface. Through the eyes of X-ray telescopes, however, the scene becomes electric. Bursts of light radiate outward, loops of plasma glow with fierce intensity, and shock waves ripple across the corona. The flare is not just light, but a symphony of radiation, each wavelength telling a different part of the story. And what a story it is. The plasma heated by reconnection can soar to tens of millions of degrees, hotter than the Sun's core itself. Particles caught in the flare are flung outward with astonishing energy, racing along magnetic highways that stretch into space. Some of these particles reach Earth in minutes, disrupting radio signals and triggering protective measures aboard satellites. Others travel farther, slipping into the vastness of the solar system, tiny messengers of the Sun's hidden storms. It is worth pausing here to appreciate the elegance of this process. All around the universe, nature is constantly searching for balance, for lower energy states. On Earth, this might be a landslide cascading down a mountain, or a lightning bolt snapping through the sky. On the Sun, it is magnetic reconnection, a rearrangement of tangled forces into something simpler, achieved through a sudden blinding flare of energy. What feels violent and chaotic is, in reality, nature finding equilibrium in its own spectacular way. For scientists, studying the birth of a solar flare is a challenge not only of scale but of speed. These events happen quickly and unpredictably, and they occur in conditions too extreme to reproduce on Earth. This is why spacecraft like the Solar Dynamics Observatory and the Parker Solar Probe are so valuable, watching constantly, recording every flicker of light, and helping unravel the details of how magnetic reconnection unfolds in such a fierce environment. The better we understand it, the more we can prepare for the ways it might affect our world. Yet beyond the technical details, there is something undeniably poetic about the birth of a flare. It is a reminder that even the mightiest star can be undone by its own tangled threads, that immense power can come from lines of force rearranging themselves into something new. It is both humbling and awe-inspiring to think that our daily sunrise comes from a star capable of such sudden, dramatic outbursts. And perhaps there is something strangely comforting in that knowledge too. The Sun may seem eternal and unchanging, but deep down it is alive with motion, with tensions that build and release, with patterns that repeat yet never quite the same. Every solar flare begins as a quiet tangle of magnetism, invisible to us, until the moment comes when the knot unravels and the sky above a star lights up in brilliant defiance. It is in those moments that we are reminded of the restless nature of the cosmos, and of the extraordinary processes that keep our universe alive with energy. When a solar flare erupts, it does not simply shine in one familiar kind of light. Instead, it sends out a grand performance across the entire electromagnetic spectrum, from the longest, slowest radio waves to the shortest, most energetic bursts of gamma rays. It is a symphony of radiation, invisible to most of our senses, yet profoundly important to the way we study the sun and understand its power. To grasp this spectacle, it helps to step back and explore the spectrum itself. That rainbow of light stretched far beyond the narrow band of colours we can see with our eyes. The light we call visible is just a sliver, a thin window between roughly 400 and 700 nanometers in wavelength. To us, this range is everything. Sunsets and rainbows, the glow of a fire, the sparkling reflection on water. But for the sun, visible light is only one voice in a vast choir. When a flare erupts, it unleashes energy across every octave of that cosmic song, some detectable only with specialized instruments, others with everyday technology on Earth. At the lower energy end of the spectrum are radio waves. These are the giants of light, stretching from centimeters to kilometers in wavelength. During a solar flare, enormous bursts of radio emission can erupt, sometimes lasting for minutes or hours. These are not gentle signals either. They can be strong enough to drown out Earth-based radio transmissions, disrupting communications and navigation systems. To scientists, these bursts are invaluable. They reveal how charged particles are accelerated and how plasma waves ripple through the sun's atmosphere. It is almost as if the sun is speaking in radio static, its storms translated into crackling voices that we can catch with large antenna dishes. Moving upward in energy, the spectrum enters the realm of microwaves and infrared. While these emissions may not grab headlines like X-rays or auroras, they are part of the flare's thermal story, carrying the heat of the explosion outward. Telescopes tuned to these wavelengths allow researchers to measure temperatures and track how plasma cools after a flare. Though invisible to us, they are crucial in piecing together the puzzle of solar activity. Then comes the light we are most familiar with, visible radiation. A strong solar flare can cause a brightening on the sun's surface that, under the right conditions, might even be seen from Earth with protective filters. These visible signatures are known as white light flares, and they are relatively rare. When they do occur, they provide a dramatic reminder that solar activity is not hidden in obscure wavelengths alone. In the 19th century, astronomers with modest telescopes recorded sudden flashes in visible light, long before anyone understood the physics behind them. To the human eye, they were dazzling, like sparks on a roaring fire. Beyond visible light lies ultraviolet, a range that straddles the line between the familiar and the dangerous. Solar flares are prolific producers of ultraviolet radiation, flooding the sun's atmosphere with photons that heat and ionize gases. Ultraviolet is absorbed high in Earth's atmosphere, which protects us from harm but also means we cannot see it from the ground. Space-based observatories, however, reveal the ultraviolet sun as a writhing, luminous tapestry of loops and arcs. During a flare, ultraviolet emissions spike dramatically, reshaping the ionosphere in ways that affect radio signals and GPS. It is a reminder that invisible light can ripple through our daily lives in very tangible ways. Climb higher still, and you encounter X-rays. These are the hallmark of solar flares, a clear sign that magnetic reconnection has accelerated particles to incredible energies. When electrons slam into denser regions of the sun's atmosphere, they emit X-rays in bursts that can be detected in orbit around Earth. Spacecraft like the GOES satellites constantly monitor the sun's X-ray output, categorizing flares by their intensity into classes C, M, and X. These measurements are not only of academic interest, they serve as a real-time alert system for airlines, power companies, and satellite operators. A sudden surge in X-rays means space weather is on the move and precautions may be needed. And then, at the extreme upper end of the spectrum lie gamma rays. These are the most energetic form of light. produced when particles reach near-relativistic speeds during the most powerful flares. Gamma rays from the sun are rare and fleeting, but when they occur, they are a sign of truly explosive conditions. Detecting them requires sensitive instruments, often shared with observatories that also study cosmic gamma-ray bursts from distant galaxies. The fact that our star can produce such extreme radiation underscores the sheer scale of energy released in a flare. For scientists, teasing apart this spectrum is like unravelling the threads of a complex story. Each wavelength reveals a different chapter. Radio waves tell us about plasma waves and particle acceleration. Ultraviolet shows us how the atmosphere is heated and shaped. X-rays reveal the violent collisions of electrons, while gamma rays whisper of the most extreme events of all. Together, these signals allow researchers to reconstruct the physics of a flare in astonishing detail, even from millions of kilometers away. It is easy to forget, sitting under a blue sky or a canopy of stars, that our lives are tethered to a star whose outbursts travel across this vast range of light. When solar flares erupt, we do not simply see them. We feel them in our technology, in our communication systems, and sometimes in the auroras that brighten the night skies. For ancient peoples, the sun's light was singular and steady, but modern science has revealed it to be a many-coloured beacon, broadcasting on frequencies both familiar and hidden. There is also a certain poetry in thinking of solar flares this way, not as single flashes, but as symphonies of light playing on cosmic instruments. Just as an orchestra brings together violins, drums, flutes, and brass to create harmony, a flare brings together radio, ultraviolet, X-rays, and gamma rays to perform a piece of cosmic music. We, with our instruments and detectors, are like audience members, straining to catch every note and make sense of the melody. And perhaps the most remarkable part is that this performance happens all the time. Small flares spark daily on the sun, sending out whispers across the spectrum. Larger flares roar every few weeks or months, blasting out across space with enough energy to remind us of our star's restless heart. In listening to this spectrum, scientists have not only learned about the sun, but also about the universe at large, since many of the same processes occur in distant stars and galaxies. The sun's fireworks, then, are not limited to the flash of visible light we might imagine. They are woven through the entire tapestry of the electromagnetic spectrum, a grand and ceaseless performance that reminds us of the richness of physics at play in the heart of a star. To watch a solar flare is to witness light in its many forms, each telling a part of the story, each carrying energy across the void, and each revealing that even the most familiar star has depths we are only just beginning to understand. Solar flares come in many shapes and sizes, from gentle flickers that barely disturb the surface of the sun to colossal outbursts that send shock waves through the entire solar system. To make sense of this variety, scientists have created a classification system that organizes flares into families, each named with a simple letter. At first glance, the categories may look straightforward, C, M, and X, but behind these letters lies a scale that helps astronomers describe some of the most powerful explosions in nature. The scale is based on the amount of X-ray radiation a flare produces near Earth, measured by detectors on satellites in orbit. The Earth's atmosphere blocks X-rays from reaching the ground, which is fortunate for our safety but inconvenient for observation. For this reason, spacecraft such as the GOEE satellites act as our guardians, constantly measuring the sun's X-ray brightness and alerting us when flares erupt. The classification is logarithmic, meaning that each step up the scale represents not just a small increase, but a significant leap in intensity. At the gentlest end of the family are the C-class flares. These are the cosmic background noise of solar activity, small sparks that occur frequently but rarely cause much concern here on Earth. A C-class flare might nudge the ionosphere enough to slightly affect radio signals, but beyond that, they are mostly the sun's low-level chatter. In many ways, they're useful reminders that our star is alive and dynamic, always simmering with activity even when it seems calm from below. Next up are the M-class flares, the middle children of the solar flare family. These eruptions are about 10 times stronger than C-class events and are often associated with moderate space weather effects. They can disrupt high-frequency radio communication, especially near the poles, and occasionally trigger stronger auroral displays. While they are not catastrophic, M-class flares are significant enough that space agencies take notice, particularly if they coincide with other solar activity such as coronal mass ejections. These flares remind us that even moderate tantrums from the Sun can ripple across our planet's magnetic shield. Then there are the giants, X-class flares. These are the most powerful category, and they can be more than 10 times stronger than M-class flares. In fact, the scale does not stop at X. It continues upward with numbers that indicate just how extreme a flare is. An X1 flare is considered strong, but an X10 flare is 10 times more intense than that, and an X20 is twice as strong again. The scale has no hard upper limit, and occasionally the Sun surprises us with flares that stretch its boundaries, leaving scientists scrambling to record the extraordinary numbers. The power of X-class flares can be difficult to comprehend. These are events that release energy equivalent to billions of nuclear bombs detonating simultaneously. The radiation can ionize Earth's upper atmosphere, disrupt satellites, and even push electrical grids to the brink. For astronauts in space, unshielded exposure during one of these events would be life-threatening. Yet despite their intensity, they are also fascinating scientific opportunities, allowing researchers to probe the physics of plasma, magnetic reconnection, and particle acceleration on a scale that cannot be recreated on Earth. Over the years, a handful of famous flares have entered the record books, both for their sheer size and for the effects they caused here on Earth. One of the largest ever recorded occurred on November 4th, 2003, during a period of heightened solar activity known as the Halloween storms. This flare was so intense that it briefly overwhelmed the X-ray detectors on the GOES satellites, saturating their instruments. Later analysis suggested that it was at least an X28 flare, possibly even stronger. The outburst sent high-energy particles racing through the solar system, disrupted satellites, and forced airlines to reroute flights to avoid excess radiation exposure near the poles. Another remarkable flare took place in March 2012. It was part of a series of powerful eruptions during solar cycle 24 and was classified as an X5.4 event. While it did not cause catastrophic disruption, it was a stark reminder of how quickly the Sun can escalate its activity, going from calm to violent in a matter of minutes. Even further back in history, before modern instruments were available, scientists and observers recorded the effects of massive flares through their consequences on Earth. In August of 1972, between the Apollo 16 and Apollo 17 missions, a powerful solar storm erupted. If astronauts had been en route to the Moon during that period, they would have been exposed to dangerous doses of radiation. The timing was fortuitous, but the event highlighted the risks that solar flares pose for human exploration beyond Earth's protective magnetic field. Perhaps the most famous historical example linked to solar activity is the Carrington event of 1859. While it is primarily remembered for its enormous coronal mass ejection, it was preceded by an exceptionally bright white light flare observed by Richard Carrington and Richard Hodgson. Using their telescopes, they watched as a sudden burst of light flashed across the surface of the Sun. Within a day, the effects of the event were felt on Earth as telegraph systems sparked. Auroras danced far into the tropics, and the power of the Sun's fury was etched into human memory. Though we cannot assign it a precise class with modern measurements, it was clearly an eruption of extraordinary magnitude. What these famous flares demonstrate is that while the Sun spends most of its time in a steady rhythm, it is capable of sudden and extreme outbursts. Scientists monitor flare classes not only as academic exercises, but as vital tools for protecting our modern world. In an age where communication, navigation and power grids form the backbone of daily life, understanding whether the sun is in a C-class mood or an X-class fury matters more than ever. Yet there is also a sense of wonder in this classification system. It transforms what might seem like incomprehensible chaos into something familiar, a family of events with names and categories that we can understand. The letters may look simple, but they carry stories of storms that have brushed against our world, of instruments pushed to their limits, and of a star that is as unpredictable as it is essential. To think of solar flares as a family is to recognize their diversity, from the quiet sparks to the cosmic giants. Each class plays a role in reminding us of the sun's restless character. They are part of a spectrum of activity that links the smallest flicker of light to explosions powerful enough to rattle our entire planet. And in that spectrum, we find not only danger and disruption, but also beauty and mystery, a testament to the living energy of the star that sustains us. When the sun grows restless, its fury is not confined to the dazzling light of solar flares. Sometimes it unleashes something far larger, a colossal exhalation of matter itself that surges out into space. These events are called coronal mass ejections, or CMEs, and they are among the most dramatic phenomena in the solar system. If solar flares are sudden sparks of brilliance, CMEs are great rolling waves of plasma, vast clouds of charged particles hurled outward at breathtaking speeds. Together they form a pair of cosmic troublemakers, companions of chaos that can shape the weather of space in profound ways. It is easy to confuse solar flares and CMEs because they often occur together, but they are not the same thing. A solar flare is primarily an outburst of radiation, light across the spectrum from radio waves to X-rays and gamma rays. It is the sun shouting across space in a flash of electromagnetic energy. A CME, on the other hand, is the sun physically ejecting part of its outer atmosphere into the solar system. It is less like a shout and more like a punch, carrying billions of tons of plasma into the void. Both are born from the sun's tangled magnetic fields, but while flares are fast and bright, CMEs are vast and heavy, moving like great storms set adrift. The distinction becomes clearer when you consider their timing. A solar flare can erupt and reach Earth with its radiation in just 8 minutes, since light travels at that speed. A CME, in contrast, takes longer. These immense plasma clouds travel at speeds ranging from a few hundred kilometers per second to several thousand, which means they might reach Earth in as little as 1 day or as long as several. This delay gives scientists a chance to prepare, issuing space weather alerts that can protect satellites, power grids, and astronauts. Yet it also means the effects of a CME can be more enduring, as the storm of particles washes over Earth's magnetic field for hours or even days. The relationship between flares and CMEs is complex. Sometimes they occur together, with a flare's burst of radiation accompanying the eruption of plasma. Other times, one happens without the other, leaving scientists to untangle the subtle differences in the sun's behaviour. When they do coincide, however, the result is especially potent. The flare provides the flash, the warning shot of light and energy, while the CME delivers the main event, a barrage of particles that can buffet Earth's magnetic shield. It is a 1-2 punch, first dazzling, then disruptive. The scale of a CME is staggering. Imagine a cloud of charged particles weighing billions of tons, expanding outward until it is larger than a star itself. These clouds can stretch millions of kilometers across, carving through the solar wind like tidal waves. As they travel, they carry with them twisted magnetic fields, remnants of the sun's own. When those fields collide with Earth's magnetic field, they can reconnect and transfer energy, setting off geomagnetic storms that ripple around the globe. For humans on the ground, the effects of these storms can range from beautiful to troubling. On the beautiful side, CMEs are responsible for the most spectacular auroral displays, the shimmering curtains of green, red, and purple light that dance across polar skies. When the influx of charged particles is especially strong, auroras can spill far beyond the poles, appearing in places where people rarely see them. On the troubling side, geomagnetic storms can induce currents in power lines, interfere with satellites, and disrupt radio communications. In extreme cases, they can even trigger blackouts, as happened in Quebec in 1989, when a geomagnetic storm caused a major power grid failure that left millions in the dark. What makes CMEs particularly challenging is their unpredictability. Scientists can watch the sun's surface, map out active regions, and even detect when a flare occurs. But predicting whether a CME will follow is not always straightforward, and even when a CME is launched, it might not head toward Earth at all. Many of them sail harmlessly into space, missing us entirely. Others are directed squarely at our planet, and those are the ones that command our attention. By studying the magnetic structure of CMEs, researchers aim to forecast not only their arrival, but also their severity, a task that remains one of the great challenges of space weather science. The combined impact of a flare and a CME is something like a solar storm in full force. First comes the flare, a brilliant flash that warns of magnetic reconnection on the sun. Then, hours later, the CME arrives, a massive cloud that crashes into Earth's magnetic field. The two together can overwhelm satellites, expose astronauts to radiation, and light up the night sky with auroras that stretch to surprising latitudes. For most of us, the result is awe-inspiring beauty, but for those who manage technology and infrastructure, it is a reminder of just how connected we are to the moods of our star. In recent years, spacecraft have given us front-row seats to these events. Observatories like SOHO and Stereo have captured CMEs in exquisite detail, watching as they erupt from the sun's corona and expand into space. The images reveal vast arcs of plasma curling outward, glowing faintly in scattered light, like great wings spreading into the solar system. These observations are not just for aesthetics. They help scientists model the speed, direction, and impact of CMEs, giving Earth a better chance to prepare. The study of CMEs has also highlighted the sun's dual nature. It is both our life-giver and our occasional threat, nurturing our planet with light while occasionally throwing tantrums that ripple across our fragile systems. Yet even in its chaos there is order. The same magnetic fields that sustain the solar cycle also shape these storms. The same physics that drives flares and CMEs helps explain phenomena across the cosmos, from distant stars to nebulae to galaxies. Our star, in its restless storms, becomes a laboratory for understanding the universe. What makes this all the more fascinating is that Earth is not unique in facing these tempests. Planets throughout the solar system feel the lash of CMEs, each in their own way. Mars, with its thin atmosphere and weak magnetic field, is especially vulnerable, its upper atmosphere stripped away bit by solar storms. For worlds beyond, orbiting stars far less stable than our Sun, CMEs may determine whether life can ever take hold. In this sense, the Sun's chaos is not just our concern, but a universal story about the power of stars and their impact on the worlds that circle them. When you picture a solar flare and a CME together, think of them as different expressions of the same magnetic drama. One is a flash of light, a sudden blaze across the spectrum. The other is a tidal wave of matter, sweeping outward with momentum and weight. Alone, each can be striking, but together they remind us that the sun is a restless companion, unpredictable and alive. And while their combined effects may cause disruption, they also gift us with some of the most extraordinary sights in the natural world. Auroras that ripple like celestial curtains, reminders that even in chaos, beauty finds its way. When a solar flare erupts, it may feel like a distant spectacle, a firework display safely tucked away on the surface of the sun. Yet the reality is that the energy released in those moments does not remain confined to our star. It ripples outward across space at the speed of light, reaching Earth in just over 8 minutes. Alongside the radiation, showers of charged particles and sometimes great coronal mass ejections surge into the solar system. For Earth, wrapped in its protective layers, this cosmic storm can become both a shielded drama and at times a disruptive visitor. The first line of defense is Earth's magnetic field. Generated deep within the liquid outer core, this field forms a vast bubble around the planet called the magnetosphere. To imagine it, picture an invisible cocoon stretched into a teardrop shape by the flow of the solar wind. On the side facing the sun, the magnetosphere is compressed, while on the far side it streams out like a long tail. It is this magnetic shield that deflects much of the sun's charged particle bombardment. Without it, the atmosphere would be stripped away over time, leaving Earth as barren as Mars. When the radiation from a solar flare arrives, it immediately affects the upper atmosphere. X-rays and extreme ultraviolet light ionize atoms in the ionosphere, the region high above the surface where gases become electrically charged. This sudden ionization can disrupt radio signals, especially those that bounce through the ionosphere on long-distance journeys. Pilots, navigators, and operators of communication systems may suddenly find static replacing clarity, as if the sun has briefly turned the sky into a noisy amplifier. If a coronal mass ejection accompanies the flare, the story grows even more dramatic. The cloud of plasma slams into the magnetosphere, compressing it like a drumhead struck by a hammer. In those moments, Earth's magnetic field lines bend, twist, and reconnect, transferring energy into the upper atmosphere. This is when geomagnetic storms arise, and the results cascade across the planet in ways both beautiful and hazardous. High in the polar regions, the charged particles spiral down along magnetic field lines, colliding with atoms of oxygen and nitrogen in the atmosphere. These collisions release light, painting the sky with ribbons of green, red, and violet. The auroras are the most visible and enchanting sign that a storm from the sun has reached Earth. Entire night skies can glow with shifting curtains of light, a dance of physics and beauty that has inspired mythologies and stories for millennia. In strong storms, auroras creep far south into regions where people rarely see them, offering surprise encounters with the sun's restless energy. Yet alongside this beauty lies a more practical concern. The same magnetic surges that create auroras can also induce currents in the ground. Power lines, pipelines, and long electrical grids act like antennas, picking up these currents and sometimes overloading transformers. In March of 1989, a geomagnetic storm triggered by a CME plunged the province of Quebec into darkness for 9 hours, as the electrical grid collapsed under the strain. It was a sobering reminder that space weather, for all its beauty, has teeth. Satellites orbiting above the atmosphere face their own challenges. A storm can heat the upper layers of the atmosphere, causing it to expand slightly. This increases drag on satellites in low Earth orbit, shifting their trajectories and sometimes shortening their lifespans. Navigation satellites, so vital for GPS, can suffer disruptions as their signals pass through a disturbed ionosphere. Communication satellites can experience electrical charging on their surfaces, leading to malfunctions. For astronauts aboard the International Space Station, solar storms mean retreating into shielded areas to minimize radiation exposure. Future explorers heading to the Moon or Mars will need even more protection, as they will leave behind Earth's magnetic umbrella. A solar flare's radiation can also affect high-frequency communication used by aircraft, especially on polar routes where signals must pass through regions strongly influenced by the magnetosphere. Airlines sometimes reroute flights to avoid these disruptions and to reduce passenger and crew exposure to increased radiation. It is a small but clear way in which the sun storms ripple into the routines of human life. What makes these effects both fascinating and challenging is their variability. A small flare may pass almost unnoticed, while a major flare coupled with a powerful CME can ripple across technology worldwide. Unlike weather on Earth, which we can watch roll in across the horizon, space weather arrives with less warning and unfolds across scales that are difficult to imagine. Scientists studying these storms rely on spacecraft parked in strategic positions, such as the Solar and Heliospheric Observatory, which can watch the sun and the solar wind in real time. These sentinels give us precious minutes to hours of warning before a solar storm strikes, time enough to adjust satellite orientations, reroute flights, and prepare power grids. Despite the potential for disruption, there is something humbling about witnessing the reach of these storms. The sun is 150 million kilometers away, yet its moods can ripple across our atmosphere and technology with ease. It is a reminder of our planet's delicate place in the cosmic web, shielded by a magnetic field and atmosphere that act like guardians against a star's occasional fury. Without them, solar storms would strip away our protection and lay bare the fragility of life. In the end, the interaction of solar flares with Earth is a story of balance. The magnetosphere deflects and absorbs, the atmosphere glows and protects, and human ingenuity adapts and prepares. Most of the time, these storms bring little more than a gentle aurora shimmering across polar skies. On rarer occasions, they ripple through our technological networks, testing the resilience of a civilization bound to the power of electricity and communication. In both cases, they remind us that we live not in isolation, but within the ever-shifting breath of the sun. There is a certain poetry in this arrangement. A star, unimaginably large and distant, breathes out storms of light and plasma. A planet, small and fragile, responds with glowing skies and occasional flickers in its machines. It is an ancient dance, one that has played out for billions of years, long before humans walked the earth or built power grids to feel its impact. To live beneath this stormy relationship is to share in the drama of the cosmos, to recognize that our nights are painted not only by stars, but also by the invisible hands of solar storms reaching across the void. When storms from the sun reach Earth, they do not always announce themselves with disruption or danger. Sometimes they arrive like painters brushing luminous strokes across the canvas of the night sky. These brush strokes are the auroras, shimmering curtains of light that ripple and dance in shades of green, violet and crimson. They are the most visible and enchanting signs of geomagnetic storms, a reminder that even in moments of cosmic violence, beauty finds its way to Earth. The origin of this spectacle lies in the particles carried on the solar wind. When a solar flare or coronal mass ejection hurls charged particles toward our planet, they follow the invisible guide rails of Earth's magnetic field. These rails bend toward the poles, funneling electrons and protons downward into the upper atmosphere. There, at altitudes of about 100 to 300 kilometers, the particles collide with atoms of oxygen and nitrogen. The collisions excite the atoms, giving them extra energy, which they later release as light. It is the same principle that powers a neon sign, except the sign in this case is a sky stretching across thousands of kilometers. The colors of the aurora are dictated by the atoms involved and the altitude of the collisions. Oxygen, abundant in the upper atmosphere, is responsible for the familiar green glow that dominates most auroral displays. When oxygen is struck at higher altitudes, it can emit red light, giving the sky a rare and dramatic crimson hue. Nitrogen, when excited, produces purples and blues, often appearing at the edges of the glowing curtains. Together these colours weave into luminous tapestries, sometimes smooth and flowing, sometimes jagged and flickering like ghostly flames. For those who live under the auroral ovals, the ring-shaped regions around the poles where auroras are most common, the lights are part of life's rhythm. In places like Alaska, Scandinavia and Canada, auroras are frequent visitors, turning long winter nights into natural light shows. Yet during powerful geomagnetic storms, the auroral curtains spread farther, spilling into latitudes where they are rarely seen. History records moments when auroras glowed as far south as the Caribbean, bewildering observers who had never imagined the sky could behave in such a way. It is no wonder that auroras have inspired mythologies across cultures. the Sami people of northern Europe spoke of the lights as energies of departed souls, urging quiet reverence when they appeared. In Inuit traditions, the auroras were thought to be spirits playing ball in the sky with a walrus skull. Norse mythology imagined them as reflections from the shields and armour of Valkyries guiding the fallen. In medieval Europe, auroras were sometimes seen as omens of war or disaster, their blood-red hues interpreted as signs of coming strife. Each culture, gazing upward at the mysterious lights, found its own meaning in their shimmering presence. Today, science provides an explanation, but the magic has not vanished. If anything, understanding the physics makes the beauty even deeper, knowing that each flicker is the signature of a charged particle travelling across millions of kilometres before colliding with an atom in the upper atmosphere adds layers of wonder. The aurora becomes not just a spectacle but a story, the visible thread of a journey that began in the heart of the sun. The auroral curtain is not a still image, it moves and shifts as though alive. Sheets of light ripple across the sky, folding and unfolding like celestial drapes caught in a cosmic breeze. Spirals twist into arcs, and sudden bursts flare before fading into softer glows. To watch an aurora is to see the magnetosphere breathing, responding in real time to the stormy energy arriving from space. No two displays are ever the same, each one a unique expression of the dynamic relationship between sun and earth. Beyond their beauty, auroras are also useful scientific tools. By observing their patterns, scientists can learn about the strength of geomagnetic storms, the flow of charged particles, and the structure of Earth's magnetic field. Satellites and ground-based instruments work together to track auroral activity, offering clues about the space weather unfolding above our heads. In a way, the auroras are like glowing gauges, measuring the impact of the sun's tantrums on our atmosphere. There is, of course, another side to these lights. Their very presence signals that charged particles are flooding into Earth's upper atmosphere, an event that can disturb radio communication, navigation signals, and satellite systems. To those who depend on technology, auroras are not just a show, but a warning that the sun's influence is reaching deep into the planet's electromagnetic environment. Yet for most people on the ground, the disruption goes unnoticed, leaving only the spectacle to enjoy. To witness a strong aurora firsthand is to feel both humbled and uplifted. Standing under a sky ablaze with shifting colours, you're reminded that Earth is not separate from the cosmos, but woven into its fabric. The air above your head is alive with energy that began 93 million miles away, transformed by invisible fields into light that drapes across the night. It is a connection both intimate and grand, a cosmic reminder stitched into the sky itself. Perhaps the greatest gift of the auroral curtain is its dual nature. Born of storms that can threaten our technology and challenge our preparations, it manifests to our eyes as beauty. What begins as turbulence in the sun's magnetic fields ends as silent light dancing above frozen forests or icy seas. It is a transformation from chaos to calm, from disruption to wonder. And in that transformation, we are reminded of the strange balance that governs our universe, that even in the most violent processes, moments of astonishing grace can emerge. So when the auroral lights appear, it is not only a treat for the eyes, but a whisper of the sun's story. It is the tale of a storm that began with tangled magnetic fields, travelled across space, collided with Earth's shield, and finally revealed itself in curtains of light. To look upon an aurora is to see the invisible made visible, to watch the breath of a star woven into the sky. And in that glow, we find not only science and spectacle, but a quiet reminder that beauty often arrives from the most unlikely of origins. On a late summer morning in the year 1859, an English astronomer named Richard Carrington was standing at his telescope, sketching sunspots as he did most days. The sun was entering one of its restless moods, and Carrington was intent on documenting the patterns. As he observed, something extraordinary unfolded before his eyes. A brilliant flash of white light erupted across the face of the sun, so intense that it outshone the dark sunspots he was tracing. Carrington had, without knowing it at the time, become the first person in history to directly observe what we now call a solar flare. What followed in the days ahead would etch his name into both astronomy and human history. Within hours of Carrington's observation, Earth began to feel the effects of an immense solar storm. The initial blast of radiation disturbed the upper atmosphere, but it was the coronal mass ejection that truly transformed the world below. Hurtling toward Earth at a speed far greater than typical solar storms, this CME carried with it billions of tons of plasma and magnetic fields, twisted by the sun's turmoil. When it struck, the impact was unlike anything recorded before or since. The auroras of that storm were astonishing. From the northern hemisphere to the tropics, skies lit up in hues of green, crimson and violet. Reports from the time described the glow as bright enough to read a newspaper at night. In the Rocky Mountains, miners awoke in the small hours, thinking dawn had come, and began making breakfast. In the Caribbean, sailors marvelled at curtains of light rarely seen so far south. For people in cities and towns across the world, the auroras were both terrifying and beautiful, interpreted by some as omens of great change. But the storm's most dramatic effects were felt not in the sky, but on the ground, in the humming wires of the telegraph system. Telegraphy was the cutting-edge technology of the mid-19th century, a web of copper lines stretching across continents, carrying messages faster than any horse or ship. As the storm surged across Earth's magnetic field, electrical currents were induced in these long wires. Suddenly, operators found their instruments sparking and crackling with surges of energy. Some were shocked as sparks leapt from their equipment. Others reported that even with batteries disconnected, messages could still be sent, powered purely by the storm's geomagnetic energy. One operator in Boston wrote that the atmosphere was so charged with electricity that the current came in great shocks, and sparks flew in every direction. The incident was as disruptive as it was surreal. Telegraph offices caught fire, lines were damaged, and communication networks faltered under the strain. Yet in a curious twist, the same storm that caused destruction also demonstrated the raw power of natural electricity. For the first time, humanity saw in stark detail that the sun's tempests could reach across 93 million miles and directly interfere with human technology. The Carrington event, as it became known, remains the most powerful geomagnetic storm on record. Its significance has only grown with time, not only as a scientific milestone, but as a sobering thought experiment for modern civilization. In 1859, the most advanced systems on Earth were telegraph lines. In the 21st century, our world is woven with technology far more delicate. Satellites orbiting above, global positioning systems guiding everything from airplanes to agriculture, vast electrical grids powering entire nations, and undersea cables linking continents. A storm of Carrington's magnitude striking today would be a challenge on a scale far greater than anything faced by telegraph operators with sparking wires. Scientists often use the Carrington event as a benchmark, asking what it would mean if such a storm happened now. Studies suggest that modern power grids, with their vast interconnected networks, are vulnerable to geomagnetically induced currents. A storm of that strength could overload transformers, trigger widespread blackouts, and take months or even years to fully repair. Satellites exposed above Earth's protective atmosphere could be damaged or disabled by surging radiation. Navigation systems might falter, communication links could collapse, and financial networks dependent on precise timing might grind to a halt. It is not an exaggeration to say that a true Carrington-scale storm today could touch nearly every aspect of modern life. This is why the event has become such a focus for space weather science. It is both a cautionary tale and a natural laboratory, a reminder of what our star is capable of. astronomers have scoured ice cores and tree rings for signs of past solar storms, looking for traces of radioactive isotopes created by intense cosmic events. These studies suggest that storms like Carrington's may occur every few centuries, though the exact frequency remains uncertain. Another storm of comparable strength has not been recorded since, though in July of 2012, a massive CME erupted from the Sun and narrowly missed Earth's orbit. Had the planet been in the line of fire, the outcome might have been uncomfortably similar to that of 1859. The legacy of Richard Carrington's observation also lives on in the way we study the Sun. His chance recording of that brilliant flare was the spark that connected solar activity with terrestrial effects. It marked the dawn of space weather as a science, a field that now spans fleets of satellites and global networks of observatories. Every time a modern scientist studies solar storms, every warning issued to power companies or airlines, every aurora forecast, all of it traces back to that moment when Carrington looked through his telescope and saw a sudden burst of light. Yet beyond the science, there is something profoundly human in the story of the Carrington event. Imagine the miners in the Rockies, bewildered as night turned to false dawn. Picture telegraph operators watching sparks leap from their machines as if the wires had come alive. Envision sailors in the Caribbean gazing at colours in the sky they had never known possible. For all of them, the sun revealed itself not as a distant lamp but as a restless force, intimately connected to their lives. In the quiet of our modern world, lit by electric bulbs and tied together by invisible signals, it is easy to forget that connection. The Carrington event is a reminder that we live beneath a star that can, with a single storm, change the rhythm of life on Earth. Its auroras were beautiful, its sparks unsettling, and its memory enduring. As scientists continue to study our sun, they do so with the knowledge that Carrington's storm was not an anomaly but a possibility, one that could come again. And so the story of 1859 is more than history. It is a tale that links past to present, a warning wrapped in beauty, and a reminder that our planet's calm nights and steady days are gifts granted under the watchful and occasionally stormy gaze of the sun. In July of the year 2012, our planet narrowly dodged what could have been one of the most disruptive natural events in modern history. The sun, in a fit of activity, unleashed a massive coronal mass ejection, a solar storm so powerful that scientists later compared it to the legendary Carrington event of 1859. But in this case, fortune was on our side. Earth was not in the storm's direct path. Instead, the blast sailed through the very spot where our planet had been just a week earlier. Had the timing been different, the world might have awoken to a morning where satellites went silent, power grids faltered, and communications faltered across the globe. This near miss is a sobering reminder of the fragility of our technology. Unlike the mid-19th century, when sparks from telegraph wires caused alarm but little lasting damage, our 21st century civilization is woven through with vulnerable systems. Satellites orbiting Earth provide everything from navigation signals to weather forecasts, communication links, and financial timing. Global positioning satellites in particular are delicately balanced, broadcasting signals that can be disrupted or drowned out by the energetic particles hurled at Earth during a storm. A direct hit from a CME as powerful as the one in 2012 could have disabled dozens of satellites in orbit, leaving vast swathes of technology inoperative. The threat extends beyond space. On the ground, power grids that span continents are particularly susceptible. Geomagnetic storms induce currents in long electrical lines, pushing transformers and substations to their limits. During the Quebec blackout of 1989, a relatively moderate storm managed to collapse an entire regional grid in less than 2 minutes. Engineers worked for hours to restore power, but that storm was nowhere near the magnitude of Carrington or the 2012 event. In a storm of that scale, transformers could be damaged beyond repair, leading to blackouts that might last not hours or days, but months. Replacement of such massive components is not quick or easy, and the ripple effects would touch everything from hospitals to banking systems. The vulnerability of satellites is equally stark. High-energy particles from solar storms can charge the surfaces of spacecraft, causing electrical discharges that fry delicate electronics. They can degrade solar panels, reducing a satellite's ability to generate power. In severe cases, entire satellites can be lost. In 2003, a series of solar storms during what came to be called the Halloween storms temporarily disabled dozens of satellites, disrupted GPS for hours, and even caused the Japanese AD-EOS-2 satellite to fail permanently. Those storms were significant, but still less powerful than the 2012 near miss. For astronauts, the danger is even more personal. On Earth, we are shielded by both the magnetic field and the atmosphere, which absorb the brunt of solar radiation. Astronauts aboard the International Space Station are more exposed, but the station itself and special shielding offer some protection. Beyond low Earth orbit, however, the risks increase dramatically. A solar storm of Carrington magnitude could expose astronauts on a mission to the Moon or Mars to dangerous, even lethal doses of radiation within hours. Space agencies monitor the Sun closely for this reason, ready to move astronauts into better shielded areas if a storm erupts. The 2012 event is not the only brush with danger in recent times. Scientists studying tree rings and ice cores have found evidence of other extreme storms in history, such as one around the year 775 and another around 993, both leaving radioactive signatures that suggest bursts of solar activity far stronger than anything observed in the modern era. These discoveries hint that the Sun is capable of producing far greater tempests than we have experienced in recorded history, storms that could test the limits of human resilience. Warnings of space weather today come from an array of spacecraft positioned strategically between Earth and the Sun. The Solar and Heliospheric Observatory, the Solar Dynamics Observatory, and the newer Parker Solar Probe all contribute to our understanding of how flares and CMEs form and travel. Satellites parked at the L1 Lagrange point, about 1.5 million kilometers toward the Sun, provide crucial advance notice of incoming storms. When a CME is detected, scientists can model its speed, trajectory, and magnetic orientation, issuing alerts to power companies, airlines, and satellite operators. Sometimes this buys us hours of preparation, sometimes only minutes, but it is far better than facing a storm unprepared. Despite these advances, there is an unsettling truth. Predicting solar storms is still an imperfect science. Unlike hurricanes, which can be tracked across oceans, CMEs emerge from the Sun with little warning, and their precise impact on Earth depends on complex details of magnetic fields that are hard to measure. Even with our most advanced models, we cannot yet forecast storms with the accuracy we would like. This means that humanity remains somewhat at the mercy of solar weather, a reminder of our planet's vulnerability under the gaze of its star. The possibility of another Carrington-level storm lingers as both a scientific curiosity and a societal concern. Engineers and policymakers have debated how to harden infrastructure, from developing transformers less vulnerable to geomagnetic currents to creating satellite systems with built-in resilience. But progress is slow, often weighed against costs and competing priorities. In the meantime, every major storm that brushes against Earth is a rehearsal of sorts, a warning that the Sun does not always keep to its calm rhythms. For most of us, the idea of a solar storm feels abstract, overshadowed by the familiar challenges of daily weather and earthly concerns. Yet the 2012 near miss stands as a reminder that our interconnected world could be shaken by forces that seem far removed from our lives. Imagine waking up one morning to find that GPS no longer functions, communication networks are patchy, banking systems are offline, and the electrical grid has gone dark. It would not take long for the ripple effects to become profound. That possibility is not science fiction, but a natural hazard written in the history of our planet and in the restless behaviour of our star, and so the near misses and warnings serve a dual purpose. They caution us about what could be lost, but they also inspire awe at the delicate balance that allows our civilization to thrive beneath a temperamental star. Each flare and CME that sails harmlessly past is both a relief and a reminder. Relief that Earth has been spared, and reminder that one day our luck may run out. The Carrington event taught us that the sun's storms can reach across space and alter the course of human history. The storm of 2012 whispered that such a moment might come again. The question that lingers, quietly but insistently, is whether we will be ready when it does. High above our heads, far beyond the clouds and the thin veil of atmosphere, an entire fleet of silent sentinels keeps watch on the sun. They are our guardians of the sky, spacecraft designed to study, monitor, and anticipate the moods of our restless star. For all the sophistication of modern technology, from satellites to smartphones, our world remains deeply dependent on understanding the whims of the sun. This is why agencies like NASA, the European Space Agency, and research groups across the globe have built a vigilant system, one that blends science and protection into a single mission: to watch the sun, always. The importance of these watchful eyes becomes clear when you consider how quickly the sun can change. A solar flare erupts in minutes, sending its light to Earth in under 10 minutes. A coronal mass ejection may take a day or two, but once it is on its way, the clock is ticking. For Earth, preparation is everything. Power companies may need to adjust grids, airlines might reroute polar flights, satellites must switch into protective modes, and astronauts need to find shelter. Without forewarning, a storm could blindside our civilization. With forewarning, its impact can be managed. One of the most enduring guardians is the Solar and Heliospheric Observatory, or SOHO, a joint project between NASA and ESA launched in 1995. Parked at the L1 Lagrange point, about 1.5 million kilometers from Earth toward the Sun, SOHO has provided a constant stream of data for decades. Its instruments allow scientists to study the Sun's interior, its surface, and its outer atmosphere, the corona. But perhaps its most famous contribution is its ability to spot coronal mass ejections, capturing their vast arcs of plasma as they burst from the Sun and expand into space. With SOHO, scientists can track the speed and direction of these ejections, giving Earth precious time to prepare if one is heading our way. Another critical observer is the Solar Dynamics Observatory, or SDO, launched in 2010. If SOHO is the watchtower at distance, SDO is the close-up observer, watching the Sun in high-definition detail across multiple wavelengths. Its images reveal the Sun in extreme ultraviolet, showing loops of plasma twisting, sunspots brewing, and flares erupting in exquisite clarity. The data from SDO helps scientists understand the mechanics of solar activity, from the roots of magnetic reconnection to the evolution of active regions. Its continuous stream of images has also brought the Sun closer to the public, with visuals so striking that they often look like works of cosmic art. In 2018, NASA launched perhaps the most daring of the Sun's guardians, the Parker Solar Probe. Unlike SOHO and SDO, which watch from afar, Parker dives directly into the Sun's outer atmosphere, swooping closer than any spacecraft before it. At its closest approaches, it travels at speeds exceeding 430,000 miles per hour, fast enough to fly from New York to Tokyo in under a minute. Protected by a cutting-edge heat shield, Parker endures temperatures of over 1,000 degrees Celsius to sample the plasma and magnetic fields of the corona. By flying into the furnace, Parker is helping answer long-standing mysteries, such as why the corona is so much hotter than the Sun's surface, and how particles are accelerated to such extreme energies. Together, these missions form a layered defense system. SOHO scans for incoming CMEs, SDO monitors the birth of flares and tracks magnetic activity, and Parker dives into the very heart of the storm to reveal its secrets. They are complemented by other spacecraft as well, such as the twin stereo probes, which provided unprecedented three-dimensional views of the Sun and the European Space Agency's Solar Orbiter, launched in 2020 to study the Sun from unique angles, including high-latitude views of its poles. Each spacecraft has its own specialty, yet they all contribute to the shared goal of keeping humanity informed about the Sun's changing moods. It is not just a matter of curiosity. The data gathered by these spacecraft feeds directly into space weather forecasting, much like satellites monitoring hurricanes feed into terrestrial weather reports. Agencies like NOAA's Space Weather Prediction Centre and the European Space Agency's Space Weather Coordination Centre analyse this data, issuing alerts to industries and governments. In an age when a single solar storm can affect airlines, military operations, GPS navigation, and even the global economy, this vigilance is essential. The global nature of the effort is worth noting. While NASA and ESA often take the spotlight, other countries also contribute to this celestial watch. Japan's Hinode spacecraft has revealed detailed images of solar magnetic fields. India's Aditya L1 mission, launched to the same strategic vantage point as SOHO, has joined the lineup of solar sentinels. Russia and China have their own observatories and ground-based solar telescopes, such as the Daniel K. Inouye Solar Telescope in Hawaii, add further depth to our understanding. Solar science is one of those rare arenas where collaboration often trumps competition, for the storms of the sun recognise no borders. What makes this system of guardians so impressive is not just their technical ability but the philosophy they embody. They reflect an understanding that while humanity cannot control the sun, it can at least learn to anticipate its moods. They also remind us of the delicate balance we live within, dependent on the sun for every drop of energy, yet vulnerable to its sudden bursts of temper. Each spacecraft is like a lighthouse, casting its beam across the solar seas, warning us of storms before they arrive on our shores. At the same time, these missions inspire awe beyond their practical value. The images and discoveries they provide show us the sun in ways no human eyes could ever see directly. They reveal a star alive with motion, loops of plasma soaring higher than Earth's diameter, eruptions that stretch into space like cosmic tsunamis, and a corona glowing with ethereal light. To watch these scenes is to realize that our star is not a static sphere but a dynamic, breathing entity, as restless as it is radiant. The guardians of the sky do more than protect. They connect us to the sun in intimate ways. They remind us that every sunrise is the visible surface of a story far deeper and more complex. They show that the calm daylight we enjoy is woven with magnetic storms, nuclear fusion, and plasma fields that stretch millions of kilometers into space. And by keeping vigil, they ensure that we can marvel at this beauty, while also preparing for its occasional fury. One day, a storm like the Carrington event or the 2012 near-miss may again set its sights on Earth. When it does, the spacecraft and scientists watching the sun will be our first line of defense, giving us the warnings needed to brace ourselves. Until then, they continue their quiet watch, orbiting in silence, measuring every flicker and flare, guardians of a star that is both life-giver and tempest. And in their data, they carry not just protection, but wonder, proof that even as we shield ourselves from the chaos of the cosmos, we are also drawn deeper into its mystery. Astronauts live in a realm where Earth's protections grow thin. On the surface of our planet, we are wrapped in layers of shielding we rarely think about. The magnetic field that deflects charged particles, and the atmosphere that absorbs harmful radiation. Together, they make life not only possible but comfortable. For those who venture beyond this shield, however, the environment becomes harsher. Solar flares, with their bursts of high-energy particles and radiation, represent one of the greatest natural hazards for human beings in space. On board the International Space Station, astronauts still enjoy some measure of protection. The station orbits about 400 kilometers above Earth, which is high enough to float in microgravity, but still low enough to remain largely inside the magnetosphere. The magnetic field, though weaker at that altitude, deflects many of the charged particles that a solar storm sends toward our planet. Even so, astronauts on the station are not completely immune. When solar flares erupt, instruments on the ISS detect increased radiation levels, and crews retreat to better shielded areas of the station, often near water supplies or specialized materials that help absorb the energy. For missions lasting months, this exposure is carefully monitored, because cumulative radiation can increase the risk of cancer or damage to sensitive tissues like the eyes. The real challenge emerges when humanity steps beyond this magnetic cocoon. Lunar missions, such as those carried out during the Apollo era, carried astronauts outside Earth's magnetic field entirely. Fortunately, no major solar flares struck during the days when Apollo crews walked on the moon's surface or travelled through deep space. In fact, one of the most powerful storms of the 20th century occurred in August of 1972, between the Apollo 16 and Apollo 17 missions. Had astronauts been en route to or from the moon during that storm, they would have been exposed to potentially lethal doses of radiation. The fact that timing spared them remains one of space exploration's lucky coincidences. Radiation exposure from solar flares can be severe because of the speed and energy of the particles involved. Protons and electrons accelerated by magnetic reconnection can reach Earth in less than an hour after a major flare, delivering doses of radiation far above background levels. Unlike X-rays or gamma rays, which can be blocked by thick shielding, these particles penetrate materials more easily, requiring dense protection or creative strategies to reduce exposure. For astronauts in deep space, the difference between safety and danger can come down to how quickly they can find shelter. Future missions to the Moon and Mars must grapple with this problem in earnest. On the Moon, astronauts will work and live in an environment with no atmosphere and no magnetic field. A sudden solar storm could turn a routine surface operation into an emergency. Shelter will be essential, perhaps in modules covered with layers of lunar regolith for shielding, or in specially designed storm shelters within habitats, surrounded by water tanks or other dense materials. Engineers are already planning such features into future lunar bases, aware that radiation is not a distant risk but a constant companion. For Mars, the challenges are even greater. A mission to the Red Planet would mean months of travel through interplanetary space, far from Earth's protective fields. During this journey, astronauts would be vulnerable to both solar flares and the steady rain of galactic cosmic rays, which are even more penetrating. The spacecraft itself must serve as a shield, but adding heavy protection is difficult when every kilogram of material launched carries enormous cost. Scientists are exploring options such as arranging water supplies, fuel, or other essential materials around crew habitats to double as radiation shielding. There is even research into active shielding, using generated magnetic fields to mimic Earth's protective bubble, though such technology remains experimental. Monitoring is a vital part of protection. Space agencies rely on satellites to provide warnings of solar storms, giving astronauts hours or even minutes to prepare. If a flare is detected and a particle storm is on the way, crews can retreat to storm shelters within their spacecraft or base. These shelters are designed to be compact, heavily shielded areas where astronauts can remain for the duration of the storm, which typically lasts a day or two. While cramped and inconvenient, such precautions could mean the difference between manageable exposure and a life-threatening dose. The dangers are not limited to long-term health risks. Intense radiation can cause acute radiation sickness if doses are high enough, leading to nausea, fatigue, and damage to organs. In the harsh environment of space, where medical care is limited, such an event could jeopardize an entire mission. The psychological impact of knowing that a storm could arrive with little warning also weighs heavily. Astronauts train extensively to handle emergencies, but the invisible nature of radiation makes it an especially unsettling threat. Yet despite these risks, humanity continues to push outward. Part of what makes solar flares so daunting is also what makes them scientifically fascinating. They are reminders that space is not empty but alive with energy, a place where even the calm glow of the sun conceals immense power. In preparing to face them, astronauts and engineers are also deepening our understanding of the sun itself. Every storm monitored, every shelter tested, and every mission planned brings us closer to living safely beyond our home planet. There is also reassurance in knowing that strategies already exist to manage these dangers. The International Space Station, though not beyond Earth's shield, provides valuable lessons in radiation monitoring and protective design. Future lunar bases may incorporate underground habitats, using natural shielding to great effect. Mars missions will carry storm shelters and redundant systems, ensuring that no crew faces the sun's tempests unprepared. Bit by bit, humanity is learning to live with the sun's moods, adapting technology, and planning with the recognition that our star will not change its nature for us. To imagine astronauts bracing against a solar storm is to picture one of the most dramatic confrontations in space exploration. A human being, fragile and finite, standing against the restless fire of a star. Yet it is not a hopeless contest. With knowledge, preparation, and ingenuity, the dangers of solar flares can be managed, if never entirely eliminated. In that balance lies both the challenge and the triumph of venturing beyond Earth. The line of fire may be daunting, but it is also the frontier. To explore space is to accept that our sun, the very source of life, is also a source of danger. For astronauts, the glow of solar flares is both a warning and a call to resilience. And for the rest of us, watching from the safety of Earth, their journeys remind us of the extraordinary courage required to live beneath a sky that is, in truth, never entirely calm. The sun, for all its fiery turbulence, follows a rhythm. At first glance it may seem steady, rising each morning and setting each night without fail. Yet when studied closely it reveals a cycle, a kind of heartbeat that waxes and wanes over time. This rhythm is the solar cycle, a roughly 11-year pattern that governs the number of sunspots, the frequency of solar flares, and the overall temperament of our star. Like a great clock in the sky, it ticks forward in ways that shape space weather, and by extension, life on Earth. The story begins with sunspots. These dark blemishes on the sun's surface are not holes or burns, as they were once imagined, but regions of intense magnetic activity. Their darkness comes from being cooler than the surrounding plasma, though they are still searingly hot by human standards. Sunspots are the visible markers of the sun's magnetic restlessness, and their numbers rise and fall in tune with the solar cycle. At the peak of the cycle, called solar maximum, the sun's face can be crowded with dozens of sunspots at once. At the trough, or solar minimum, the surface may appear spotless for days or even weeks. This rise and fall is not random. In the mid-19th century, an amateur astronomer named Samuel Heinrich Schwabe discovered that sunspots seem to follow an approximately 11-year rhythm. His careful daily observations revealed that the sun's activity was not constant but periodic, pulsing with an unseen clockwork. Later research showed that this cycle is tied to the sun's magnetic field, which flips polarity every cycle. North becomes south, and south becomes north, creating a grand magnetic oscillation that repeats itself again and again. Each full magnetic reversal actually takes about 22 years, but because sunspot activity peaks halfway through, the visible cycle appears as an 11-year rhythm. During solar maximum, when sunspots are abundant, solar flares and coronal mass ejections also become more frequent. This is because the tangled magnetic fields that create sunspots are also the breeding grounds for flares. More sunspots mean more opportunities for magnetic reconnection, and more reconnection means more storms. Solar maximum is the sun at its most dramatic, a period when Earth experiences more auroras, more radio disruptions, and more reminders of our star's volatile side. In contrast, solar minimum is a quieter phase. Sunspots may vanish entirely, flares become rare, and the sun's face looks serene. Yet even in these lulls, the sun is never truly still. Subtle flows and magnetic patterns continue beneath the surface, slowly winding the magnetic field in preparation for the next cycle. It is a cosmic inhale and exhale, one phase feeding into the next with steady inevitability. The solar cycle is more than just an astronomical curiosity. It has real consequences for our world. Space weather forecasting depends heavily on knowing where we are in the cycle. Satellite operators, airlines, and power grid managers all pay attention to predictions of solar maximum, when the chances of disruptive storms are highest. For astronauts planning deep space missions, the timing of a solar cycle can influence safety, since periods of high activity bring greater risks from flares and particle storms. Even climate studies take the cycle into account, as small fluctuations in the sun's output can subtly influence Earth's energy balance, though they're not the driving factor behind long-term climate change. Tracking the cycle has also given scientists insight into the deeper workings of the sun. The magnetic field that drives it is generated by processes in the solar interior, often described as the solar dynamo. Convection currents of plasma rise and fall, while the sun's equator spins faster than its poles, twisting magnetic field lines into knots. Over time, the field becomes so tangled that it must reset, flip in polarity, and starting the cycle anew. This dynamo process is complex and still not fully understood, but studying the cycle is one of the best windows we have into the magnetic heart of our star. The cycle does not always follow a perfectly neat 11-year pattern. Some cycles are stronger, with many sunspots and violent storms, while others are weaker and more subdued. Occasionally, the sun slips into long lulls, such as the Maunder minimum between 1645 and 1715, when sunspots nearly disappeared for decades. During that time, parts of Earth experienced cooler temperatures, leading to speculation about the connection between solar activity and climate. Modern research suggests that while solar cycles can nudge Earth's climate, they are not the primary drivers of long-term trends. Still, the Maunder minimum serves as a reminder that the sun's rhythms can vary in ways that ripple across our planet. Today, scientists monitor the solar cycle with precision unthinkable to Schwaber and his 19th century telescope. Networks of observatories track sunspots daily, satellites measure magnetic fields and radiation, and computer models attempt to predict the strength and timing of future cycles. Each new cycle is announced with great interest, as scientists mark the emergence of the first sunspots with reversed magnetic polarity, the telltale sign that a new phase has begun. Solar Cycle 25, the current one, began in 2019 and is expected to peak around the middle of this decade. Predictions initially suggested it might be relatively weak, but early activity has shown it could be stronger than expected. As the cycle ramps up, scientists and forecasters are watching closely, not just to marvel at the sun's activity, but to prepare for the potential storms it may unleash. For all its complexity, the solar cycle has a certain elegance. It is the pulse of a star, a rhythm written into the fabric of plasma and magnetism. To study it is to listen to the heartbeat of the sun, slow by human standards yet vital to the life of our planet. Without it, solar activity would seem random and unpredictable. With it, we can see patterns, anticipate change, and find reassurance that even in chaos, nature often keeps a rhythm. There is also a poetic quality to this cycle. The sun, constant in our daily lives, reveals itself to be dynamic when viewed over years and decades. Its cycles remind us that constancy is often an illusion, that beneath steady appearances lie patterns of change. Just as seasons shape life on Earth, the solar cycle shapes the weather of space, bringing times of calm and times of storm. To look at the sun with this perspective is to see it not as static, but as alive, breathing in cycles of magnetism and light. In the end, the solar cycle is both a scientific tool and a cosmic story. It explains why auroras are more common in some years than others, why flares seem to arrive in bursts, and why our star sometimes appears crowded with spots and sometimes bare. It is the rhythm by which the sun lives, and in its steady beat we find both knowledge and wonder. Watching the cycle unfold is like following the verses of a song, one that has been playing for billions of years and will continue long after our brief time beneath its glow. Our sun may sometimes seem tempestuous, but compared to many stars scattered across the galaxy, it is a model of moderation. Solar flares that rattle our technology or spark auroras on Earth are significant to us, yet on a cosmic scale they are often mild. Other stars are prone to tantrums far greater, releasing what astronomers call super flares, eruptions hundreds or even thousands of times more powerful than anything the sun has ever unleashed. These outbursts not only challenge our understanding of stellar physics, but also raise profound questions about where life might be able to survive in the universe. Superflares were first confirmed in the early 21st century with the help of space telescopes like Kepler, which measured the brightness of distant stars with extraordinary precision. Kepler's mission was primarily to discover planets by watching for the tiny dips in starlight as worlds crossed in front of their suns. But in the process, it also recorded sudden, enormous spikes in brightness, some lasting hours, others days. These were not planets but flares, so intense that they dwarfed anything in the sun's history. For a world orbiting such a star, the effect would be catastrophic. Intense radiation flooding the atmosphere, stripping away protective gases, and showering the surface with dangerous particles. One of the most notorious flare-prone stars belongs to the family of red dwarfs. These are the most common stars in the Milky Way, smaller and cooler than the Sun, yet vastly more abundant. Their cooler temperatures mean that the habitable zones around them, the regions where liquid water might exist, are much closer to the star than Earth is to the Sun. A planet in this zone would orbit so near its star that a year might last only a few days or weeks. The problem is that red dwarfs are notorious for their violent flares. Their magnetic fields can be twisted and tangled with astonishing intensity, releasing storms that make our sun's activity look like a candle compared to a bonfire. For exoplanets orbiting red dwarfs, this creates a dilemma. On the one hand, red dwarfs are stable in terms of lifespan. They burn their fuel slowly, living for trillions of years, far longer than the sun. On paper, they seem like ideal hosts for life, offering vast amounts of time for biology to take root and evolve. But their constant flaring may strip away atmospheres, sterilize surfaces, and leave planets barren. Radiation doses from superflares could be hundreds of times greater than what Earth experiences even in the strongest solar storms. Without thick atmospheres or strong magnetic fields, such planets may never hold on to the conditions necessary for life. Astronomers have observed examples of these stellar tantrums in vivid detail. Proxima Centauri, the closest star to the Sun, is a red dwarf, and in 2016 it was discovered to host a planet within its habitable zone. Excitement about Proxima b was high. Could our nearest stellar neighbour be home to life? But in 2018, astronomers watched Proxima Centauri unleash a flare 10 times brighter than anything its star usually produces, blasting its planet with ultraviolet and X-ray radiation. If Proxima b has an atmosphere, it is almost certainly battered relentlessly. The prospect of life there, once tantalizing, seems far less likely in light of these violent outbursts. Other red dwarfs have shown similar behaviour. The star Adelionis, just 16 light-years away, has been observed to produce flares that outshine its normal brightness by large factors. Another, EV Lacertae, produced a flare in 2008 that was so powerful it would have posed serious hazards if Earth had been orbiting that star instead of the Sun. For these stars, superflares are not rare anomalies, but part of their regular behaviour, constant reminders that not every star provides a safe harbour. Yet superflares are not limited to red dwarfs. Even stars more like our Sun can occasionally unleash them. Observations suggest that younger stars, with faster rotation and stronger magnetic fields, are more prone to these giant eruptions. In fact, some astronomers believe that in the early days of the Sun's life, billions of years ago, it may have been more active and flare-prone than it is today. If so, early Earth would have faced harsher conditions, and the resilience of life may have been tested from the very beginning. The fact that life arose anyway is a testament to biology's tenacity, or perhaps to the protective powers of Earth's atmosphere and magnetic field. The study of stellar flares also connects directly to the search for habitable worlds. When we find exoplanets in the so-called habitable zone, we must remember that distance from the star is only part of the equation. If the parent star is prone to frequent superflares, that zone may not be habitable at all, at least not for surface life as we know it. A planet could orbit in the right temperature range and still be sterilized by constant blasts of ultraviolet and X-ray radiation. The search for life among the stars, then, is not just about planets, but also about the temperaments of their suns. There are possible workarounds, of course. Life might persist beneath the surface of such worlds, shielded by rock or water. Subsurface oceans, like those suspected on Europa or Enceladus in our own solar system, could provide refuge from a stormy star. Atmospheres rich in protective compounds, or strong planetary magnetic fields, could also blunt the worst effects of stellar flares. Some scientists argue that flares might even play a paradoxical role in sparking chemistry, providing bursts of energy that drive the formation of complex organic molecules. In this way, what looks like destruction could also serve as creation, seeding the first steps of life in hostile conditions. Still, for civilizations that might one day emerge, frequent superflares would pose immense challenges. Imagine a world where the sky brightens violently every few days, where electronics short out regularly, and where radiation storms force entire societies underground. Such a world would be difficult to tame, no matter how advanced its inhabitants. In this sense, the calm moderation of the Sun is one of Earth's greatest blessings. We orbit a star that flares often enough to remind us of its power, but not so violently as to endanger our survival. It is a delicate balance, and one that may be rare in the galaxy. When astronomers look beyond our Sun, they see a spectrum of stellar personalities. Some stars are quiet and steady, others volatile and fiery. Our Sun sits somewhere in between, lively enough to keep us on our toes, but mercifully restrained compared to its more tempestuous cousins. The study of flares beyond the Sun not only reveals the physics of magnetic storms, but also reframes our place in the cosmos. Life as we know it is not only a product of water, chemistry and time, but also of the temperament of the star we orbit. The next time you hear of a solar flare rattling satellites or painting auroras across polar skies, consider this. On many worlds around other stars, such events are not rare disturbances but constant realities. For those worlds, the dream of life may be forever out of reach, undone by the tantrums of their suns. And in that contrast lies a quiet gratitude, for in the cosmic lottery of stars we drew one that, despite its occasional outbursts, allows life to flourish under its glow. The Sun, as the giver of light and warmth, has always been tied in human imagination to the fate of Earth's climate. For ancient cultures, a bright sun meant abundance, while a dim or hidden sun meant famine. In the modern era, as we study solar flares and the Sun's restless activity, the question arises, can these outbursts truly influence the climate of our planet? The answer, like much of science, is nuanced. Solar activity does play a role, but it is subtle, and often smaller than myths or popular claims suggest. To begin, it is helpful to distinguish between weather and climate. Weather is immediate and local, a storm here, sunshine there. Climate is the long-term pattern of these events, shaped by global energy balances. Solar flares and their companions, coronal mass ejections, affect space weather dramatically, but their influence on Earth's climate is more indirect. A single flare, no matter how powerful, does not change Earth's temperature or alter seasons. Its effects are fleeting, mostly limited to radio blackouts or auroras. Climate, by contrast, is a matter of decades and centuries. To find the Sun's role in shaping it, we must look not at isolated flares but at long-term patterns of solar activity. One of the clearest markers of solar activity is the 11-year solar cycle, measured by the rise and fall of sunspots. When sunspots are abundant, solar activity is high, and the sun emits slightly more energy. When they vanish during solar minimum, the output decreases a little. The difference is small, about 0.1% in total solar energy. Yet even that small variation can subtly nudge Earth's climate system. During periods of sustained low activity, like the Maunder minimum in the 17th century, Earth did indeed experience cooler conditions. This era coincided with what is known as the Little Ice Age. When winters in Europe were harsher, rivers froze more often and glaciers advanced. The connection, however, is not as simple as cause and effect. The Little Ice Age was influenced by many factors, including volcanic eruptions that injected aerosols into the atmosphere and natural variations in ocean circulation. The sun's reduced activity likely contributed, but it was only one thread in a larger tapestry. This example highlights the challenge. Solar variability matters, but it is never the sole driver of climate. It interacts with other forces, amplifying or damping them, often in ways that are difficult to untangle. Modern myths sometimes exaggerate the role of solar activity. Claims that current global warming is caused primarily by the sun rather than greenhouse gases have been carefully examined and found wanting. Satellite measurements over the past 4 decades show that while Earth's temperature has risen sharply, solar output has not increased in the same way. In fact, if anything, the sun's energy has shown a slight downward trend during this period. The warming we observe today cannot be explained by solar cycles or flares. It matches far more closely with the rise in greenhouse gases from human activity. The consensus among climate scientists is clear. The sun influences climate, but the dominant force in recent warming is us. This does not mean the sun is irrelevant. Solar variability can still affect Earth in subtle ways, especially regionally. For example, changes in ultraviolet radiation during solar cycles can alter the chemistry of the stratosphere, influencing ozone concentrations. These changes can in turn affect atmospheric circulation, shifting jet streams or patterns of rainfall. Some studies suggest that solar cycles may play a role in phenomena like the North Atlantic Oscillation, which influences winter weather in Europe. These effects are often small compared to other drivers, but they illustrate how solar activity ripples through the complex machinery of Earth's atmosphere. Beyond direct radiation changes, solar storms may also influence climate indirectly by affecting cosmic rays. Cosmic rays are high-energy particles that constantly bombard Earth from beyond the solar system. During periods of high solar activity, the strengthened solar wind shields Earth more effectively, reducing the number of cosmic rays reaching the atmosphere. Some researchers have proposed that this reduction could influence cloud formation, as cosmic rays help seed tiny droplets in the upper atmosphere. If fewer clouds form, Earth would warm slightly. If more form, it would cool. While intriguing, this theory remains debated. The effect, if real, appears to be subtle, not the dramatic driver that some popular accounts claim. It is worth remembering that the sun is far from a static lamp. Over billions of years, its output has slowly increased, a fact that has shaped Earth's history in profound ways. Early Earth received less energy from the young sun, yet still managed to stay warm enough for liquid water, likely thanks to a thicker greenhouse atmosphere. In the far future, as the sun continues to brighten, it will eventually push Earth out of the habitable zone entirely. On geological timescales, the sun is the ultimate arbiter of climate. On human timescales, however, its variations are gentle nudges compared to the powerful influence of greenhouse gases and other planetary processes. The story of solar flares and climate is therefore one of scale. Flares are dramatic, but they are momentary. They can disrupt technology, paint the skies with auroras, or send astronauts into storm shelters, but they do not alter the trajectory of climate. The longer solar cycles, with their small variations in energy, can influence patterns over decades or centuries, adding texture to the climate record. Occasionally, extended lulls like the Maunder minimum may line up with colder eras, yet when it comes to the rapid warming of recent decades, the sun is not the leading character. There is a quiet lesson in this. The sun, vast and powerful, sets the stage for life on Earth, providing the energy that drives winds, rains and seasons. But within that stage, the fine details of climate are shaped by many forces, including the gases we release into the atmosphere. The myths that place all responsibility on the sun overlook the evidence, but the truth is no less fascinating. Our climate is the product of a delicate interplay between stellar rhythms, volcanic outbursts, ocean currents, and human choices. Thinking of solar activity in this context brings both perspective and humility. The sun can send storms that dazzle and disrupt, but its fingerprints on climate are light and subtle. It is a reminder that while we are bound to the rhythms of our star, we are not passengers without agency. Our actions, small in cosmic terms, can tip the balance of climate far more sharply than the sun's cycles do today. In the end, the connection between solar flares and climate is not one of direct control but of gentle influence. The sun breathes in cycles, and Earth responds with shifts that weave into the greater story of climate history. Understanding this relationship enriches our view of both star and planet. It shows us that while myths of solar dominance may be appealing, the reality is more intricate, a balance of stellar rhythms and earthly dynamics. And in that balance, the beauty of science lies not in grand exaggeration, but in quiet truths, patiently revealed over time. Picture an ordinary morning. You wake to the glow of a digital alarm clock, check your phone for messages, and perhaps glance at the news while the coffee brews. All of this depends on invisible networks, satellites circling high above, power grids humming across continents, and precise signals beamed across the sky. Now imagine that in the middle of such a day, without warning, the sun unleashes a flare of extraordinary power. Within minutes, radiation floods the upper atmosphere, and within hours a colossal wave of plasma crashes against Earth's magnetic shield. The lights flicker, and then, for much of the world, they go out. This scenario is not science fiction, but a possibility, however rare. Astronomers call it a megaflare, an eruption far beyond the usual CM or even X-class events we experience today. The sun has never released such a flare in recorded history, but evidence from other stars shows it is possible. Kepler telescope data has revealed super flares erupting from sun-like stars, each releasing hundreds of times more energy than the most powerful solar storms we have known. If our star produced such an event, the consequences for modern civilization would be profound. The first sign would be an intense surge of radiation arriving in less than 10 minutes. X-rays and ultraviolet light would ionize the upper atmosphere, causing radio blackouts across much of the globe. High-frequency communication, essential for ships and aircraft, would fall silent. Navigation systems relying on radio signals bouncing through the ionosphere would fail. Airlines flying near the poles might suddenly lose contact, forcing immediate diversions. To the average person, the disruption might at first be invisible, hidden in the networks that quietly keep the world connected. But the real storm would come later. A vast coronal mass ejection, hurled into space by the flare, would reach Earth within 1 to 3 days. This wave of plasma, weighing billions of tons, would slam into the magnetosphere, compressing it and setting off geomagnetic storms of unprecedented intensity. Auroras would blaze across the skies, visible not just near the poles but possibly across much of the inhabited world. Streets in cities like Rome, Delhi, or San Francisco might glow with green curtains of light, a sight both breathtaking and ominous. As the storm continued, electrical currents induced in long power lines would surge through transformers and substations. Unlike a thunderstorm that cuts power for a few hours, this would be a continental-scale event. Transformers could overheat and fail, some irreparably. Power grids, delicately balanced systems designed for stable flows of current, could collapse under the pressure. Within minutes, lights would blink out not just in neighborhoods but across entire regions. In some areas, power might return after a day or two. In others, critical infrastructure could remain dark for weeks or even months while replacement equipment is built and installed. Satellites would fare no better. High-energy particles from the flare would bombard electronics, shorting circuits and degrading solar panels. Some satellites would shut down to protect themselves. Others might fail entirely. The loss of GPS alone would ripple into countless areas of daily life, from agriculture and banking to shipping and smartphone navigation. Communication satellites might be disabled, severing television signals, internet links, and phone calls. Weather forecasting, reliant on fleets of orbiting instruments, would suddenly falter just as Earth's atmosphere was being agitated by the storm. Air travel would face unprecedented disruption. Without reliable navigation and communication, flights across oceans and polar routes would be delayed, diverted, or grounded altogether. Supply chains, already fragile in modern economies, would stumble. Ports and logistics systems reliant on satellite tracking would find themselves working blind. In hospitals, backup generators would hum to life, but longer-term outages could strain resources. Even mundane tasks like withdrawing money or filling a car with fuel would become unexpectedly difficult, since banking and pumps rely on networks tied to electricity and precise timing signals. The scale of the disruption would depend on how well societies are prepared. Engineers know the vulnerabilities and have explored protective strategies. Grid operators can reduce load, satellites can enter safe modes, and astronauts can retreat into shielded areas. But preparation is costly, and megaflares are rare. The balance between readiness and risk often tips toward caution in theory, but complacency in practice. A flare strong enough to overwhelm all defences would test even the best prepared systems. For individuals, the experience might feel both surreal and ancient. Without power, nights would darken to starlit skies. Without satellites, communication would slow to the pace of local networks. In a sense, the flare would push us backward in time, reminding us how dependent we have become on delicate technologies. The glow of auroras overhead would be a strange counterpoint. The most advanced society humanity has ever built brought to its knees, while nature paints the skies with a show that would have amazed ancient ancestors. Science fiction often imagines apocalyptic scenarios with flames and ruins, but the reality of a megaflare would be quieter and stranger. It would not destroy cities or topple buildings. Instead, it would unravel the threads of modern life, the silent signals, invisible flows of electricity, and constant hum of machines that we rarely notice but always rely upon. The disruption would be measured in lost connections, stalled systems, and the humbling recognition of how much we depend on the calm of our star. Yet even in this sobering vision, there is resilience. Power grids can be rebuilt, satellites replaced, and communication networks restored. The true challenge would be enduring the weeks or months of disconnection, adapting while systems slowly recover. Communities might rediscover older rhythms, relying less on instant communication and more on local networks of trust. The experience would be uncomfortable, even frightening, but not the end of civilization. Humanity has endured storms before, both literal and figurative, and it would endure again. Still, the lesson of imagining such an event is clear. Our sun, though life-giving and constant, is not always gentle. The same nuclear engine that fuels photosynthesis and warms our days can also hurl storms powerful enough to rattle our world. Most of the time, these storms are minor inconveniences, producing auroras and little more. But once in a great while, the sun might remind us that it is not just a steady light in the sky, but a star capable of immense energy. Contemplating a megaflare is both unsettling and awe-inspiring. It shows how fragile our systems are, yet also how extraordinary our achievements have been, to build a world so interwoven that the moods of a star 93 million miles away can ripple through every aspect of daily life. It invites us to prepare, not with fear, but with respect for the cosmic forces that surround us. And it leaves us with a question worth pondering. In the event of a flare that silences our machines and paints our skies, what would we learn about ourselves in the quiet that follows? There is a certain poetry in knowing that the sun, so steadfast in our daily lives, is also capable of sudden fireworks. To us on Earth, it rises with quiet regularity, bathing the world in a soft golden glow. Yet in truth it is restless, its surface alive with plasma, its magnetic fields coiling and snapping, its outbursts flashing into space with a brilliance beyond comprehension. Solar flares are its fiery punctuation marks, reminders that even the most familiar star is not simply a constant lamp, but a living, dynamic being. When we look at these flares through the eyes of telescopes, the imagery becomes almost dreamlike. Great arcs of plasma trace invisible magnetic lines, glowing in ultraviolet light like the strokes of a painter who works in fire. Loops taller than Earth rise and collapse, crackling with energy. In X-ray images, the sun's surface appears as a stormy canvas, bursting into bright knots that bloom and fade in minutes. The calm golden circle we glimpse in daylight is, in truth, a cauldron of motion and fire, a restless sea with flames shaped by magnetism. There is beauty in this, but also fragility. A solar flare on its own cannot scorch Earth or burn away the atmosphere, but its reach is long. Its radiation sweeps across the void in minutes. Its particles can rattle our satellites and touch the wires that hum with our electricity. A flare reminds us how dependent we are on invisible protections, the magnetic field that diverts much of the storm, and the atmosphere that shields us from harmful radiation. Without these, life would be exposed to the full force of our star's temper. In a way, solar flares are both threat and gift. They create auroras that ripple in ethereal curtains across the sky, luminous dancers born of chaos. They disrupt, but they also inspire, painting the heavens with reminders of our cosmic connection. The same flare that might trouble a satellite can also send rippling veils of green and red shimmering above frozen forests, a natural spectacle that leaves viewers in awe. This duality, danger and beauty intertwined, is at the heart of what makes solar flares so compelling. To reflect on solar flares is also to reflect on scale. They dwarf human experience. A flare can release energy equivalent to billions of nuclear explosions, yet it is but a flicker on the face of a star 1 million times the size of Earth. What feels enormous to us is, in cosmic terms, only a minor outburst. Still, their effects reach across 93 million miles, brushing against our daily lives. That paradox, vast power expressed in fleeting bursts and fragile life responding from afar, captures the delicate balance of our existence. The sun has been doing this for billions of years, long before there were eyes to notice. Its storms raged in the deep past, perhaps shaping the early atmosphere of Earth, perhaps nudging the chemistry that made life possible. Its rhythm of cycles has continued through the ages, a steady drumbeat of activity written into the fabric of the cosmos. Now, with instruments orbiting above our planet, we see these events in exquisite detail. We can watch as light ripples outward, as particles stream into space, as the surface flares with sudden brilliance. The fact that we can both fear and admire these outbursts is a measure of how far we have come. Fragile creatures watching a star with tools of glass and metal. And yet, for all our science, solar flares are also reminders of humility. They show us that the universe does not conform to our schedules or our conveniences. The sun flares when it must, a star driven by physics indifferent to human concerns. All we can do is watch, predict, and adapt. In this sense, flares are a teacher. They remind us that control is an illusion, and that survival depends not on mastery but on understanding. There is a strange comfort in that. To know that our place in the cosmos is fragile is also to know that it is precious. Earth is shielded not by chance alone, but by structures, magnetic and atmospheric, that are the products of its deep history. These protections make our planet a rare sanctuary in a universe where solar tempests often strip worlds bare. Mars, once warmer and wetter, lost much of its atmosphere to storms like these. Other exoplanets circling stars more violent than ours may never hold on to life at all. By comparison, our world seems delicate but also profoundly fortunate. When poets speak of fire in the heavens, they often imagine distant stars twinkling or meteors streaking across the night. Yet solar flares are the true fireworks of the sky, hidden from human eyes yet spectacular through the lenses of modern science. They embody the paradox of the sun, giver of life, but also a reminder of power far beyond us. Each flare is a whisper from the star at the centre of our system saying, "I am constant, but I am not still." The poetic fireworks of solar flares invite us to see beauty in energy itself. Light is not just illumination, but a message across the void. Radiation is not just hazard, but a reminder of the sun's vitality. Plasma loops are not only storms, but sculptures, drawn in lines of glowing fire across the sky. In them we glimpse not just the mechanics of magnetism, but the artistry of nature. Science and poetry converge here, in the realization that physics can be as awe-inspiring as myth. To lie under a starry sky, unaware of the flares erupting far beyond our vision, is to be both sheltered and ignorant. To study them, to see their arcs and flashes through telescopes, is to awaken to the drama of our own star. And to reflect on them is to recognize the fragility of our existence, protected by layers of shield while the sun continues its eternal dance. The poetic fireworks of solar flares are not meant to frighten but to remind. They tell us that beauty and danger are not opposites but companions. They teach us that fragility is not weakness but a condition of life, one that makes each moment under the sun all the more precious. And they invite us, each in our own way, to marvel at the paradox of a universe where fire can destroy and fire can sustain, where a storm can darken the skies of technology and at the same time paint the heavens with light. The sun is not silent. It does not speak in words but in patterns of light, bursts of radiation and rhythms that unfold across centuries. Its storms, far from being meaningless tempests, are part of a deeper story, one that reveals the inner workings of a star. Solar flares are chapters in this narrative, each one a glimpse of the sun's magnetic heart, a reminder that our familiar star is alive with motion and change. To study them is to listen carefully to a storyteller whose language is fire. At its core, the sun is powered by nuclear fusion, turning hydrogen into helium in a furnace of unimaginable heat and pressure. But the flares we see on its surface are not directly about fusion. They are the outward signs of magnetism born from the restless churning of plasma in the sun's outer layers. Just as the rhythm of a heartbeat tells us about the health of a body, the rhythm of flares tells us about the state of the sun's magnetic field. In this way, they are more than explosions, they are signals, offering clues to the deeper processes hidden beneath the surface. The story begins with the solar dynamo, the engine that drives the sun's magnetism. Deep inside, convective currents rise and fall like boiling water, carrying heat outward from the interior. The sun also rotates differentially, with its equator spinning faster than its poles. These motions twist and stretch magnetic field lines, tangling them into knots that eventually snap and reconnect. Each flare is a punctuation mark in this ongoing process, a moment when the magnetic field releases pent-up energy in a brilliant flash. The sun's language is magnetic, and flares are its exclamation points. By watching these events, scientists have pieced together not only the nature of solar activity, but also the broader life story of stars. Our sun is middle-aged, about 4.5 billion years into a life that will last perhaps 10 billion years in total. Its flares, while impressive to us, are relatively modest compared to the tantrums of younger stars. Observations of other stars show that when they're young, rotating quickly and burning fiercely, their magnetic activity is far more violent. They unleash super flares that make even the strongest solar eruptions look tame. Over time, as stars slow their spin and settle, their flares become gentler, their tempers cooler. In this way, the frequency and power of flares tell a story of stellar aging. Our sun's flares also reveal its cycles. Every 11 years or so, the number of sunspots rises and falls, reflecting the flip of the magnetic poles. During solar maximum, when sunspots are abundant, flares become frequent. During solar minimum, they fade. This cycle is not just a curiosity, it is a heartbeat, a repeating rhythm that has persisted for as long as humans have watched the skies. By studying the timing and intensity of flares, scientists track the health of the solar cycle, watching for signs of stronger or weaker activity. This knowledge does not just serve Earth's needs, it also feeds into our understanding of how stars evolve in magnetic terms. Flares also tell us about the layers of the sun itself. Different wavelengths of light, from radio waves to X-rays, reveal different parts of the solar atmosphere. A flare that brightens in ultraviolet shows us how the chromosphere responds. One that shines in X-rays points to energetic collisions in the corona. By stitching together these signals, astronomers build a map of how energy moves through a star's outer layers. The sun is, in effect, writing its autobiography in light, and we are learning to read it. The story grows even richer when we look beyond our own star. Red dwarfs, the most common stars in the galaxy, flare with astonishing frequency, their magnetic fields more tangled than the sun's. These flares reveal both the dangers and possibilities of life around such stars. Giant stars nearing the ends of their lives flare less often, but their magnetic fields still shape their outer atmospheres. Each star, through its activity, tells us something about where it stands in its life cycle. By listening to their flares, we can chart not just individual stories, but the broader epic of stellar evolution. There is also a poetic side to this storytelling. To think of flares as mere technical data is to miss part of their meaning. They are luminous bursts, fleeting yet powerful, like the sudden flash of inspiration in a human life. They remind us that constancy is an illusion. Beneath the steady glow of the sun lies a restless heart. In this way, flares speak to both science and philosophy. They tell us about plasma and magnetism, but they also remind us of impermanence, of the hidden energy that underlies what seems calm. The lessons carried in these flares extend far beyond academic study. They shape our understanding of habitability in the universe. A planet orbiting a flare-prone star may be bathed in radiation, its atmosphere stripped away, its surface sterilized. Another, orbiting a quieter star like the Sun, may enjoy long stretches of stability in which life can flourish. Flares thus become part of the cosmic calculus, determining where in the galaxy life can emerge and endure. By listening to these stellar stories, we also learn something about ourselves, about how rare and precious our circumstances may be. The sun's role as a storyteller is not confined to the distant cosmos. On Earth, solar flares have already written chapters in human history. The Carrington event of 1859, with its blazing auroras and sparking telegraph wires, is one such chapter. Modern near misses, like the 2012 storm that slipped past Earth's orbit, are another. These are reminders that the story is ongoing, that we are participants in it, not just observers. Each flare adds to the narrative of how humanity and its star are intertwined. In the future, as humanity ventures outward, flares will continue to shape our story. They will dictate how we shield spacecraft, design habitats, and plan journeys beyond Earth. They will remind explorers that even as they leave their home planet, they remain bound to the rhythms of the sun. The storyteller will still be speaking, and the challenge will be to keep listening. What makes this story remarkable is that it is told in silence. Solar flares have no sound in the vacuum of space, no voice that human ears can hear, yet through light and magnetism they speak across 93 million miles, carrying messages from a star to its planets. By learning to interpret these signals, we draw closer not just to understanding the sun, but to appreciating the language of stars themselves. In the end, to see a solar flare is to glimpse the sun's inner self expressed in fire. It is to witness a star revealing its magnetic heart, one burst at a time. Each flare is a word, each cycle a paragraph, each epoch a chapter in a story billions of years long. And we, brief inhabitants of a small planet, have the privilege of listening, of turning the sun's fiery language into knowledge and knowledge into wonder. The sun is not only our star, it is also our storyteller, narrating the tale of stellar life in a voice written in light. The sun is always there, steady in the sky, so familiar that it is easy to forget how restless it truly is. To us, it appears patient and calm, a dependable clock marking the rhythm of days and seasons. Yet when seen more closely, it is revealed as a star that never sleeps. Its surface is alive with storms of plasma, its magnetic fields twist and snap, and its corona breathes outward in a constant wind. It is at once our protector and our threat, both gentle and explosive, a paradox at the centre of our lives. Every sunrise feels like a promise, a quiet assurance that the star will rise again tomorrow and the world will be lit and warmed. That constancy is comforting, but it is also deceptive. The sun is not fixed but dynamic, always in motion, always on the edge of turbulence. Granules the size of continents boil across its surface. Arcs of plasma, taller than our entire planet, leap upward and collapse in fiery loops. Invisible fields tangle beneath its surface, waiting for the moment when they will break and reconnect in sudden flares. This ceaseless activity is not the exception but the norm. The sun's stillness is only an illusion born of distance, and yet it is this restlessness that sustains life. The light streaming from the sun fuels photosynthesis, driving the growth of plants that form the base of Earth's ecosystems. Its warmth keeps oceans liquid and climates habitable. The solar wind, though it sometimes surges with storms, also shapes the boundaries of the solar system, pushing back the constant drizzle of cosmic rays from deep space. In this sense, the sun is a guardian, wrapping Earth in both energy and protection. But the same processes that sustain us also create moments of danger. Solar flares and coronal mass ejections are reminders that our star is not under our control. A flare that seems small on the sun can rattle radio signals across half a planet. A coronal mass ejection, hurled outward with billions of tons of plasma, can buffet Earth's magnetic field so hard that power grids falter and satellites fail. The sun does not choose to threaten us. It is simply being what it is, a star governed by physics, unconcerned with the vulnerabilities of the life it nurtures. This dual nature, protector and threat, is what makes the sun such a compelling presence in our understanding of the cosmos. It embodies balance. Without its energy, Earth would be a frozen rock, lifeless and still. Yet with too much of its fury, life as we know it would be impossible. We exist in the delicate middle ground, a zone where the sun is generous but not overwhelming, where its storms are survivable but not absent. It is a precarious balance, one that feels at once fragile and miraculous. To call the sun patient might seem strange when one imagines the violence of flares and eruptions, but patience is a matter of perspective. On human timescales, the sun is timeless. It has shone for billions of years and will continue for billions more. Its cycles repeat across decades, its evolution unfolds over eons. A solar storm that might seem dramatic to us is, in its history, a brief flicker, no more significant than a spark struck from flint. In this way, the sun is patient, moving with the slow grace of stellar time. At the same time, it is never still. It rotates, its equator faster than its poles. Its magnetic field flips polarity every 11 years, a quiet but profound shift. It sheds particles that stream past planets and comets, sculpting tails and atmospheres. It never pauses, never truly rests. Even in its moments of apparent calm, there are flows and eddies of plasma, subtle pulses of magnetism, hidden tempests waiting to unfold. To live beneath such a star is to live in a relationship that is both intimate and vast. Its light touches every leaf, every ocean wave, every moment of human history. Civilizations have risen and fallen under its gaze, crops have flourished or failed depending on its moods, and mythologies have painted it as god, guardian, or flame. And all the while, the sun has continued its endless dance, indifferent to our stories yet central to them. Science has given us a deeper way of listening to the sun. Telescopes reveal its loops and flares in wavelengths invisible to human eyes. Spacecraft dive into its atmosphere, sampling the plasma and fields that create its storms. We now know that solar flares are not just bursts of light, but windows into the sun's magnetic heart. We understand that its cycles are not random, but shaped by the churning of plasma deep within. With each discovery, the sun becomes both more knowable and more mysterious, offering answers while raising new questions. The story of solar flares in particular captures the paradox of our place in space. They are signs of turbulence, yet they give us auroras, some of the most breathtaking spectacles on Earth. They are dangerous to astronauts and satellites, yet they teach us about the physics of stars across the galaxy. They are fleeting events, yet they echo across millions of miles, brushing against our world in ways both subtle and dramatic. Through them, we see the sun as both a source of wonder and a reminder of fragility. In reflecting on this, one cannot help but feel awe at the balance that allows us to exist. Our star, restless and explosive, could easily have been more violent, like the flare-prone red dwarfs that sterilize their worlds. It could have been less stable, offering little chance for life to take root. Instead, it sits in the middle, temperamental but survivable, stormy but nurturing. The fireworks of solar flares are part of its character, woven into the same energy that lights every dawn. To call the sun a star that never sleeps is to acknowledge both its constancy and its restlessness. It is always burning, always stirring, always shaping the environment of its planets. It is timeless in its endurance, yet restless in its expression. It is calm in the steady glow of daylight, yet explosive in the flashes that remind us of its true nature. And it is in this paradox that our place in the cosmos becomes clear. We are children of a star that is both patient and wild, sheltered and tested by its moods. As we close the journey through solar flares, what lingers is not fear but wonder. To live beneath such a star is to be constantly reminded of the grandeur of the universe. Its storms remind us of our dependence on shields we cannot see. Its light reminds us of the gift of warmth and energy that sustains us, and its fireworks remind us that even the most familiar part of our world is filled with mystery, beauty, and power. The sun never sleeps, and neither does the story it tells. It is a tale written in light and fire, a reminder that we are small yet privileged to witness the drama of a living star. Each flare, each aurora, each sunrise is part of that story, one that began billions of years ago and will continue long after our time has passed. To look up at the sun is to see not just a source of light, but a companion, patient and restless, calm and explosive, protector and threat, a star whose eternal wakefulness makes our brief lives possible. The journey through the world of solar flares is in many ways a journey into the paradoxical nature of our star. On the surface, the sun appears eternal and unchanging. It rises each morning and sets each night with such reliability that human civilizations have built calendars, rituals, and even entire world views around its steadiness. Yet beneath this appearance of constancy lies a restless heart. The sun is alive with motion, its magnetic fields twisting and snapping, its plasma roiling, its energy escaping in bursts of light and matter. Solar flares are the most vivid expression of that restlessness, sudden fireworks on the canvas of a star. Scientifically, flares are puzzles. They are the result of magnetic reconnection, a process where tangled magnetic field lines suddenly snap into new alignments, releasing energy on a staggering scale. Understanding this process fully has challenged physicists for decades, because it involves plasma, a fluid that is also a conductor, behaving in ways that are both complex and elegant. Flares tell us about the invisible architecture of the sun's magnetic field, about the mechanisms that drive stellar activity, and about the connections between our star and the wider cosmos. To study them is to step into a laboratory unlike any other, one too vast to control but rich with lessons about the very forces that shape the universe. At the same time, solar flares are reminders. They remind us of how fragile human life and technology are under the gaze of a star. A strong flare can disrupt radio signals, disturb satellites, and shake power grids. An even stronger one could, in theory, plunge modern civilization into days, weeks, or months of disconnection. The possibility is humbling, for it shows how dependent we are on invisible systems, the magnetosphere above, the power lines below, and how delicately they are balanced. Every flare, no matter how small, is a gentle nudge to remember that Earth's safety is not absolute, but contingent on shields and systems we rarely notice. And yet, flares also remind us of beauty. The same storms that send waves of radiation through space are also responsible for auroras, those shimmering curtains of green, red, and violet that ripple across polar skies. To stand beneath an aurora is to see solar activity made visible, to witness light born 93 million miles away playing across the atmosphere of Earth. This is the poetry of solar flares, that in their violence they also create wonder, that in their chaos they paint beauty, that the sun, while restless and unpredictable, also gives us moments of awe that no other phenomenon can provide. Looking at the sun this way transforms it from a simple sphere of light into a storyteller. Its flares are not random tempests but chapters in its long narrative. They tell us of magnetic fields coiling and snapping, of cycles that repeat every 11 years, of rhythms that span centuries. They speak of youth and age, reminding us that younger stars flare more violently and older stars flare less often. In this sense, each solar flare is a word in a language of fire, part of a tale billions of years in the making. We, with our telescopes and satellites, are the fortunate audience learning to read it. There is a perspective here that is both scientific and deeply human. Science shows us the mechanics, plasma flows, particle acceleration, radiation across the spectrum. Humanity brings the interpretation, awe at auroras, myths about fiery skies, concern for fragile technologies. The two are not opposed but complementary. To see solar flares only as threats is to miss their grandeur. To see them only as beauty is to ignore their power. In their dual nature, they reflect the duality of the sun itself, life-giver and hazard, steady and restless, nurturing and unpredictable. The question of how flares shape Earth is not only about immediate effects. Over the long arc of time, solar activity has helped shape the evolution of the atmosphere, influenced the habitability of planets, and determined where life can thrive in the galaxy. Worlds around flare-prone stars may be sterilized before life can begin. Mars, lacking a strong magnetic field, has lost much of its atmosphere to storms from the sun. Earth, by contrast, has retained its shield, allowing life not only to survive but to flourish. In this way, solar flares are not just storms but gatekeepers of possibility. They determine, quietly but firmly, which worlds can host life and which remain barren. And so, as we reflect on solar flares, we see them not as isolated fireworks, but as part of a larger dance. A dance of energy that stretches from the tangled fields of the sun's surface to the rippling auroras of Earth, from the fragility of satellites in orbit to the mythologies whispered by ancient cultures, gazing at strange lights in the sky. The sun's fireworks connect us to the cosmos, reminding us that our lives are woven into forces both immense and invisible. What is most humbling is the time scale. Solar flares will continue long after we are gone. They erupted before humans ever walked the earth, before the first trees grew, before life crawled from the oceans. They will continue as the sun ages, as continents shift, as species rise and fall. Eventually, billions of years from now, when the sun swells into a red giant, its activity will change, and flares will become part of a different story. But the rhythm will continue until the star's final days. In the grand scale of time, our encounter with solar flares is a brief moment of awareness, in a story that began long before us and will continue long after. And perhaps that is the ultimate gift of reflecting on solar flares: perspective. They remind us of our smallness, of the fragility of our machines and the brevity of our lives, but also of our ability to wonder, to understand, and to prepare. They show us that beauty can arise from chaos, that danger and grace can share the same origin, that even the most ordinary sunrise hides beneath it a restless star performing fireworks of unimaginable scale. As we close this journey, imagine the sun not as a silent sphere but as a dancer. Its flares are leaps of light, arcs of plasma, sudden gestures of energy that ripple across space. Earth watches from its safe distance, both participant and audience, warmed by the steady glow and dazzled by the sudden sparks. The dance is ancient, ongoing, and eternal, and we are privileged to witness it. The sun's fireworks are more than storms. They are a cosmic performance. They are puzzles for scientists, wonders for dreamers, and reminders for all of us that our place in the universe is fragile yet extraordinary. Long after our voices fade, the sun will still be dancing, flaring and shining, a star that never sleeps, carrying on its eternal story in the language of light and fire.